a lot of time, we may say decades, investigating the Neolithic Celteminar and other cultures in the Turanian lowland, and they found that many of sites of settlements of this culture was located along the contour line of circa about 200 meters above sea level in completely recently dry steppe and semi-desert of this area, whereas the settlements of the hunters and fishermen, finally also stock breeders of the Celteminar culture, typically were located directly on riverbanks or lake shores. So it was completely surprising why so many settlements are located in large distance from any identified water body. So Szymczak and Nazarov, archaeologists, I would like to stress, postulated an existence of a great paleolake or a system of paleolakes in the Turanian lowland, with the water table reaching this contour line 200 meters. Of course, if you know this area and the reconstructions of the sea or lake systems and river system in this area during Holocene, you know that nobody confirmed existence of such a large water body in this area. It is curious, but the question is still why so many settlements are located exactly along, and not only of Celteminar, but also, also another Neolithic culture are located already along this contour line. So the question asked to us was on the invitation to us was just based on the basic question: could we, using the pedagogical methods, confirm or just verify the working hypothesis on the location of settlements on the shorelines of presumed paleolake? As I told, it was very initial investigation, just few days excursion, let's say, because it was pilot study before prepared larger project. The project will concern on climate changes, not on archaeological or pedological issues, but this topic could be also involved. The study was located in the Ayakagirma side. I will say why it was selected. It is located in Uzbekistan, so east from the Caspian Sea, southeast from former Arid Sea, and the Turanian lowland, recently occupied, we may say, by Kyzyl Kums and Karakum regions. The area is just in between large rivers, Sirdarya in the north, Amudarya in the south, and there is also another large river, Zarafshan, and the oases located in the river valley. For example, Samarkand and Bukhara are well known due to historical reasons, and they are very important as agriculture areas. So the site was selected in Ayakagirma was selected as very well known and also available. So the technical aspects were important. The site is located circa about 80 kilometers north of the Bukhara oasis. We had time to locate, to prepare only few soil profiles during this time. So we created a kind of catena of sequence of profiles. The location of archaeological site is indicated with the letter A. It is now circa about 65 meters above the existing small lake, Ayakagirma Lake, and 2 kilometers away from the lake. So it is clear, it is too large distance to say that they had direct access to water. So it is absolutely impossible that they use this water directly. So probably they had access to another water body or river in this site. And it was selected because a lot of artifacts, archaeological artifacts, were found in this place, and dating of the artifacts confirmed at least two periods of settlement. So between 6 and 5.5 thousand years, calibrated years before Christ, and the second between 4 and 3,000 years also before Christ. So if we try to imagine before present, we have to add 2,000 years, but it is according to archaeological traditions, yes. And if we want to imagine the present-day climate, so mean annual temperature is circa about 15 Celsius degree, precipitation 130. Dry steppe, according to some classification, it is subtropical dry steppe, so very hot summers and very cold, dry winters. As I told, only 5 peaks. One of them, we may say control peak, located above this contour line, so in highland at circa about 260 meters. 2 pits located in archaeological site in the center and the border, and 2 located in the depression of the Ayakagitma depression, one of them just on the shore of existing small lake. Unfortunately, as I told initially, we didn't have permission for any samples. Of course, we could collect samples, but did not transport them to abroad. Yes. Finally, we got permission, but only for circa about 50 samples, up to 100 grams of sample, each sample. So you can imagine absolutely no possibility to collect boxes for micromorphology. But as I told, it is just pilot study, and I would like to show you the results, which are still quite interesting if you are talking about the Katina and the differences between soils. Methods quite variable, but we may still say basic. What is interesting, what we wanted to do here was also analysis of alkanes and sterols in separately selected organic rich samples. Just as you know, the method it is useful in reconstructing the vegetation, possible vegetation, which is very important if we have such question. We also dated the to say age. We know the difference between mean residence time and age of organic matter in soil, but we didn't find any charcoals, larger charcoals, or organic particles, betable particles. Additionally, initial mapping, geomorphic mapping, just to show spatial location and differences. Sorry, I will start with the presentation of profiles. So the first profile was located, as I told, in the upland above the archaeological site. And what is interesting in this soil profile, very few results only of those analyses made. So it consisted of sandy material with some silt addition in the topsoil, then still sandy material with some addition of fine gravels, and at the bottom, completely gravelly material. So only 10–20% of sand and silt. So we can recognize at least 2 lithological discontinuities. The uppermost part, we may say it is more or less now Aeolian, or at least rewarded by wind. The transitional is fluvial Aeolian, and the bottom is absolutely fluvial, and we may say developed in course of very high energy stream because of large stones, even boulders, rounded or sub-rounded. So it indicates that in completely different conditions if we compare the three layers. Very low content of carbon, as typical for such areas, less than 0.5% of organic carbon. pH above 8 up to 8.4.5 in the central part of horizon. Salinity, so conductivity, not very high, indicating some salinity, but not very, very high. Throughout carbonates, but as indicated in the description of soil profiles, secondary carbonates we recognized only in the topsoil, not the uppermost, but in how to say, upper horizon and inside the profile, but not below. And gypsum was present throughout the profile, very little concentrations in the upper part, but quite high in the bottom. As you can see, there is a lot of pendants, crystals, accumulations, but the crystal accumulation is the most typical for this horizon. So this is the predominant feature of this gravity horizon. So we finally classified this soil as gypsy soil due to the presence of the gypsy horizon in the profile. Calcaric indicating calcareous and skeletal material. What is also interesting, if we classify, especially if we try to apply the Russian or other local systems, the presence of this B horizon in subsoil. It is sandy material, but the B horizon was quite well developed. We apply it here according to WRB system, the qualifier Bronnikova. The classification maybe is not so important, but just the properties, features of this soil profile, especially this gravelly, rich in gravel subsoil is particularly important. Because if we move to the archaeological side, so 60 meters below lower altitude, the soil is completely different. The parent material, first of all, is completely different. It is clay throughout, or at least silty loamy, silty clay. No skeleton, even fine gravel is absent here. Even coarse sand is absent in this profile in all horizons we studied. So very fine texture of the material. Organic carbon content in the upper horizon also quite low, even if the color of the horizon was quite dark. But in the buried, thin but nearly black buried A horizons, we have up to 1.5%. So it's quite high concentration of carbon, unknown surface soils of this area. pH even above 9. I did not present the data of exchangeable cations, but the profile is throughout saturated with sodium, the dominant cation apart of calcium in this profile. Conductivity very high, even above 22 decisiemens per meter in subsoil. Carbonates present throughout, but secondary carbonates only somewhere not very common in the upper horizons, but in the subsoil when we have even up to 40% of carbonates that are nearly in primary forms in sand and silt, recognizable even under binocular, as shown previously. And gypsum throughout the profile, and in most of horizon we can easily recognize secondary gypsum. So up to 30% of gypsum in this horizon. It is very specific. So according to classification, first of all, we have to find this salinity according to the key to WRB salinity, and this is why the soil was classified as Szymczak. But as I thought, classification maybe it's not important, but here it is indicative that it is Szymczak with high content of gypsum, even in secondary form, saturated with sodium. There are quite important features we can remember. What is also interesting in this profile, there are cracks at the surface. Of course, first of all, we checked are there silicon sites or clay cutans, just to testify the presence of nitric horizon or vertic or at least protovertic properties? No, we didn't find nothing. The cracks are filled with sand, this Aeolian sand added probably recently. So in our opinion, cracks here in this clay materials just remains of tucker-like structures. which are quite common in this area, maybe not in dry steppe, but in for example, oases in floodplains of Zarafshan and on some lake shores. But such kind of structures and this clay material is more typical, more common, we may say, in these floodplain areas. So this was our opinion that this clay, gypsum-rich topsoil materials was probably formed or at least transformed on the flooding terraces. But the buried horizon and the horizons, the soil below it, is finally stratified and full in organic carbon, especially this, the sea horizons, which suggest rather the lacustrine origin of this material. The other profile we don't have time to describe in details, but it also has this similarly, no gravel, no coarse material, only fine material stratification visible very well, especially in the subsoil and the buried horizon. But in this case, we can observe that it's not one continuous homogenized horizon, but in fact there are 3 or 4 very, very thin humus-enriched layers, and there are and they are quite well preserved, indicating also the conditions of sedimentation. If we go down, jump down below the barrier, orographic barrier to the depression, Ayakagitma depression, on the sides we are on such a plane with low little inclination towards the center of the depression, towards the lake. And soils are stratified, no well-developed A horizons, no B horizon, just stratified materials throughout, nothing special. It is calcareous throughout, but no secondary carbonates. It is gypsiferous throughout, but no secondary gypsum. So it is just fluvisol, antisol according to fluent according to American terminologies, and what is interesting, it is fine textured, but at 100 centimeters, 140, you have such strata which are very coarse. Gravels, pebbles, some of them rounded, but some crushed. So it indicates probably kind of catastrophic flow during some time, because below we still have these fine textured and stratified materials. If we go down to the shore of the lake, existing lake, what we can find, we expected very thin lacustrine sediments if we hypothesized that the lake existed throughout the Holocene, so we expected through humus-rich horizon sediments. But what we found, only 45 centimeters of the soil profile above clay shales, weathered, of course, but it was clear that any material weathered soil is down to 45 centimeters only. Where are the sediments? Moreover, clay content very low. So it was absolutely surprising for us. A pH above 8, conductivity. Of course, it is not very low, but also not very high. Carbonates are present, but in primary forms. Or in lithogenic form, gypsum present also throughout, but also in primary forms, no secondary gypsum. So we may say it is typical glacial here. Calcaric, of course, and sodic, saturated with sodium throughout. Any other features are initially developed. Beautiful crust at the surface, beautiful, containing gypsum, carbonates, chlorides. But what is interesting, age of and mean residence time, 12,000 years. 12,000 years. So where are the sediments of the Holocene lake? Whereas we collected samples from the bottom sediments here, just 10 meters away of the shoreline, 600 years old. 600, because it is 1,400 calibrated anno domini, so it means only 600. So incomparable age of organic matter here and somewhere here in the soil. So according to conclusions, as I told, 15 minutes, so it is just to jump from topic to topic. As I told, soils in the Ayakagitma site, which represent the settlement of preliminary culture, located at 200 meters above oceanography, developed, we hypothesized from water sediments materials of the Holocene age, in our opinion, most probably of lacustrine flooding origin, and substantially differ from highland soils developed from Pleistocene fluvial sediments. So it is absolutely different material of water origin, not like the older fluvial sediments above. The burial of older age horizons confirm flooding and submerging of the settlement site after the first phase of settlement, because I didn't send just one word that the first portion, older settlement was connected already with this horizon, but the younger was connected, artifacts were connected with this horizon. So it indicates that something was in between the two phases, kind of flooding, covering with sediment. Tucker-like humus-rich horizon suggests the development of at least a second settlement on a kind of local flooding plain, in our opinion. Morphology and properties of soil located in this area below the archaeological site, including the analysis of volcanic stones, do not confirm the presence of large water body like lake or sea during the Neolithic period. So it seems finally that the Neolithic settlement has developed, in this case at least, on a shore of small water body closed by natural orographic barrier and fed by seasonal tributaries. Destruction of the barrier, as probably shown in the coarser material in these alluvial fans, led to disappearance of this local water body, changes in ecological status of soil, and finally this resulted in desertification of the area and probably disappearance of the settlements due to dryness, lack of water. So thank you for your attention. A few pictures from this beautiful area, interesting area.
Thank you very much, but no time for questions. So,
First, you told I have unlimited time.
yeah.
So fortunately, I rejected.
Yes. Bruce, this is our next speaker who will present geomorphic patterns in the Rangeland soil landscapes.
All right. So, as you gather by the white hair around here, I've been doing this for a little while. And one of the things that I have come to believe, and I'm not sure everyone else believes this, but we'll see, is that we know very little about soils on the Earth's surface. And I say that in the point of view that we know a lot about agricultural soils. We put all our effort into understanding agricultural soils and how they can provide food and all these other sorts of things. But areas outside of that, we basically know very little. And anytime you're mapping soils at a scale of 1 to 50,000 or greater, basically you are giving a very poor insight into what the actual soil landscape looks like. So that's the basis of my discussion today. And part of it is that it's important that we actually know a lot more about these soils. In the past, the NRCS had no interest nor were they told to understand these sort of landscapes. I mean, if you're running a cow on 50 acres, you really don't care what's the soil that is underneath it. So, but now we're starting to have to deal with the impacts of changing climate, and we're doing a lot of modeling and trying to understand the geomorphic processes in the landscapes, and this is particularly true in arid environments. There's a much greater need. Well, people are using the soils information that exists. And what I hope to show you today is that it's not just wrong, it's dramatically wrong. And at the scale that they're mapping out, really they're better off saying that they don't know anything rather than assuming that the data that they have is in any way useful for their purposes. So it's a fairly bold statement to be making to a bunch of soil scientists, so I hope you'll bear with me. All right, let's, do I change it? technology. All right, let's see. Which one do I?
Right.
One on the right, there you go. Okay, so the problem is, only in areas suitable for intensive agriculture are the soils characterized at a scale of 1 to 10,000 or less, and they probably occupy less than 10 to 20% of the surface area. So the other 80% of the land surface is poorly characterized. Soil maps consist of broadly defined taxonomic units within compound and complex soil mapping units. So the criteria they use for identifying particular soils is very broad, and you then mix that up even further by compound or combining different soil mapping parts of the landscape into complex soil mapping units. Unfortunately, getting more accurate soil maps is logistically expensive. Anybody will tell you that, even if there is any interest in doing it. And we know that there's a lot of work going on, particularly with digital soil mapping, machine learning, and various other things like that. But in 30-odd years of digital soil mapping, I have yet to see a soil map that has any relevance, I think, to things that we're doing. So digital soil mapping seems to be wandering down some sort of dark corridor and don't seem to be producing anything, I think, of great relevance to people who are trying to use soils. And I think one of the things that's really lost out of all this is the influence of geomorphic processes in soil landscapes. Our landscapes are created by dominantly fluvial processes, and the processes themselves create a pattern within the soil landscape, or create the pattern of the soil landscape. So I want to talk, maybe if we could dim the lights, some of these slides might be a little hard to see here. So I'm going to start with a couple of areas that are extremely different in terms of their climate. So we have the Camp Creek drainage in the South Island of New Zealand, an area I worked in a few years back. Just to give you some context, we have a pointer on this thing?
On the top.
The top is the pointer.
Yeah.
Oh, perfect. Okay, so this is the Alpine Fault in New Zealand, a very active fault, pops about every 350 years with a magnitude 6 or greater earthquake, so that's a really exciting thing. And this is the actual drainage of the area that I looked at. And this is what it looks like. You can see remnants of glacial activity up in here. There's a cirque up in here. There's some flattened ridge crests here. These are marine terraces. I will point out that we are some 50 miles from the ocean and 3,500 feet above sea level. So it's, and as I say, this is a fairly busy landscape. We've got rainfall of 7 meters a year, uplift rate around about 6 millimeters a year, erosion rate about 6,500 tons per kilometer per year. And what we think of, or some people think of, as a temporally controlled soil landscape. By that we mean that the soil landscape is dominated by just how long that piece of land is in place. This is the soil map, 1980. Well, this is where the Alpine Fault is. This is all the forested area, so they talk about orthic clay soils. That's about it. No big surprise, nobody has a great deal of interest in understanding a great deal more about this. I was working there with the Forest Service, and they were particularly interested in rates of erosion, in part because they believed that some of the introduced mammals that came into that country back in the 1800s was destroying the vegetation and creating a hazard or potential hazard in terms of erosion rates. That is completely bogus. The rates are so damn high that you couldn't tell the difference with the effect of the animals in there. So when I started putting in soil pits around there, I kept seeing all sorts of different types of soils. It took me a while to figure out how to group them in some sort of relevant way. And so I identified a group of soils developed on unconsolidated regolith, shallow soils developed over bedrock, and then something that you will never see on any soil map, compound soil profiles containing at least one buried soil. And for the life of me, I do not understand the aversion to recognizing and identifying buried soils and soil landscapes. I mean, I've never seen a soil map that shows them. I've never seen a soil classification system that deals with them. And so it's one of those things. And so I identified 14 different soil profile classes in this drainage base. And I'll give you an example of some of these. So this is a recent soil, an unconsolidated regolith. In terms of recent, maybe 300 to 400 years. You can see that there's very little pedogenic differentiation here. There's a bit of darkness up here with organic matter. There's a lot of organic matter in the soils. And this is just, as I say, an unconsolidated regolith. Moderately developed soils, because of the amount of organic matter in here, this O horizon's up the top here. This is an H horizon with a lot of organic material. We see some glaying occurring in here. It's so damn wet, obviously. So it's just like putting a sponge on something and that water is continually seeping in there, creating anoxic conditions and the mobilization of iron. And we see this pretty clearly in different environments here. And then you're looking at well-developed soils, and of course, the reducing conditions are very common in all of these sorts of soils. And these are also on unconsolidated regolith. This one here is actually up in the grassland, and you can see that there's a nice little iron hand forming at the base of this reduced horizon there. Well, we also see a number of different soils on shallow soils over bedrock, but relatively similar to what I've just described for the unconsolidated regolith. The reason I separated them out is I didn't have any clear idea about how quickly these sorts of soils would develop. I assumed that they would develop more quickly here because there's just not so much regolith to support them. And then we find a series of soils that have compound soil profiles in them. So you have very organic layers down in here. And these are areas that get constant deposition on a maybe 5 to 10 year basis. Those older soils there probably attain that degree of soil formation within 1,000 years. So, I mean, things are just very, very active there. And so you end up with a pattern of soils. So this is further up, quite a ways up in the basin here, but you've got these large band surfaces out here, and then these are hill slopes, obviously quite steep. I separated out these very long slopes from these shorter ones down here. These are forming by the dissection of a former glacial surface. These other ones, of course, are part of the whole drainage divide up in here. And then down here we have the deposition part of the system, and this has been stable long enough that all the soils, as shown down in here, are glade and very glade. There's a difference in terms of there's an O horizon that's almost a meter thick. And what you see here is the variability of soils imposed by the proximity of the soil to these large drainages that are dissecting. This is what it's called in the geomorphic area. These are called baenas or balinas. So anyway, you can see that as you get further and further away from the drainage here, the soils, the O horizon gets significantly thicker due to just the impounded or compounded saturated conditions. So when you're looking at soil variability, this is what it looks like. So you see those really steep hill slope systems have a wide range of soil profiles. We've got 14 different profile classes here, and about 8 or 9 of them could be found within those very complex hill slope systems. The large band surface has very little range in terms of soil properties. You don't see a lot of berry soils or anything in there. And then on that smaller hill slope system, we have a smaller range, but again, we see buried soils forming in those parts of that landscape. Okay, but now it's completely different. This is part of the Ladrone Mountains and the Siberia Wildlife Refuge, which is about 150 miles up the rift here. This is what we determined as a spatially controlled soil landscape, and I'll come back to that talk. One of the important things, I don't know, can we actually turn the light off here? It's going to be a little hard to see otherwise. And also, you can't see what I've written up there as well. Hope you don't all go to sleep in the next few minutes here. Okay, so this is the Ladrone Mountains here, which go up to about 10.5 feet. We have granitic terrain through here, mostly granitic with some metamorphosed granites and things through here. We have a large series of pediments. These things are pediments where Sediment is being transported from the mountain front over towards the depot center somewhere to the east here. These are bounded by very large faults. This is the Jita fault, which is one of the rift-bounding faults in here, and it juxtaposes 5 million-year-old sediments against 1.4 billion-year-old granites. So a lot of separation there, probably about 40 kilometers or something like that. The pediments have a granitic alluvium that's been transported across here. And then out here, we have a longitudinal fault. This is the hanging wall of the fault where the sediment is accumulating, but it is a topographic high. And this is material in here is all that granitic alluvium coming on here. We dated these surfaces, the oldest pediment up here, we dated it at 600,000 years. So we are going to look at a bunch of soils forming up here on the bedrock, and they've been forming for less than that period of time because they're lower in elevation than these surfaces here. This is the existing soil map of the area, and I'll talk about what the taxonomic units are in a minute. But one of the things that you see here is that it's really hard to understand what the basis of identifying these mapping units are. And these are definitely complex, but it would seem that they're trying to identify the different slopes here. So this is a south-facing hill slope. This is a north-facing hill slope here. That seems to be what they're trying to gather, but we'll come back to that in a minute. What you can see, these areas are dominated by bedrock. There's not a thick amount of colluvial material on them, and you can see some changes in the texture of the landscape, which I'll get to in a minute. The two soil series that are mapped in here is the Puertocito series and the Metrak series. And this is what they are. Loamy skeletal mixed mesoglyphic eustolocite largit. It's a bit of a mouthful. And then we have also loamy skeletal and argiustol formed from alluvium from tuff. So the paramaterials in both of these things are absolutely wrong. They're not volcanic rocks, and they're not from tuff. As I say, they're granites. And then the thickness of the soils being 14 inches, as we'll see in a minute, is not quite correct either. So what controls the variability of soils in this landscape? And as I hope to show you, paramaterial, slope orientation, and slope position are the three factors that really determine what you're going to find in any particular part of the landscape. So one of the first things I came across was this boulder here, which is really interesting perspective of soil formation, and that is, this is an area that has had metasomatism. You had hot fluids going through the granite at some point, which altered the concentration of biotites in the granite. And so in this one down here, you have very large biotites, and they weather out quickly, being more mafic. They weather more quickly than more silicic minerals. And so you end up with grus, which is, most people would know, is mostly quartz and feldspar crystals that have been released by the weathering out of the granite of the biotites. And then up in here, the biotites are so small that they don't have that same impact, and they don't weather as quickly. And so on the right here, we had two soils forming on a south-facing hill slope soil in small biotite, and that same south-facing slope with large biotite in it. And you can see that the soil here is about 40 centimeters thick. The one over here is about 1.5 meters thick. I'll get into that, why that is. So here's an example, two soils forming in granite, 10 meters apart, a small biotite granite here. You can see it's actually got quite almost an O horizon, but this is an AH, right? Or, sorry, almost a molar horizon, that it doesn't have the depth. But you see that the weathering, the way this rock weathers is to put large, clumpy pieces of bedrock. Whereas over here, you've got this very fine texture, well, not fine texture, but you've got this gravelly quartz and feldspar grains with the biotites weathering out in a very, very thin soil above the weathered saprolite there. These two soils are 10 meters apart. So this also plays into the idea about what is the scale of variability. Okay, I'll speed it up a bit. So this is sort of landscape on here. We also see soil continuous developed. So here we have, this is a hill slope, this is a north-facing hill slope on the the fine textured granite. And you can see that there's a horizon here, a little bit of a B, and there's a calcic horizon here. And then on the lower slope position, which is taken down here, you can see it's 1.5 meters thick, and you can see a very well developed soil there with an A horizon, good BW, a little bit of clay translocation, but not a lot, and then a calcic horizon developing there. And then on the difference between north and south facing hill slopes in here, you see these are both at the same slope position. This is the one we just looked at, 100 meters down. This is on the opposing slope in the same slope position, and you see you're hitting bedrock at around about 40 centimeters. And so, and in fact, that's the only place where you actually see a soil developed on that hill slope. So, to interpret soil variability in this type of landscape, what you need is proxy data. And in this case, we can use paramaterial. We can use, so the geology maps are reasonably accurate, a lot easier to map geology than it is to map soils in most of these areas. The slope orientation is particularly important. We can get that off of BEMs, and certainly slope position as well. So with this sort of data, you can actually make a reasonably educated guess as to what the nature of the soil landscape is going to be in that particular area. That's it. And this actually is the depot center where all that sediment is being deposited. This is a very thick package of sediments, mainly the same sort of material that we were looking at earlier. Look at the beautiful ecotonal boundary through here. This is north-facing hill slope, south-facing hill slope. And you can make you believe in proxy data at this point, right?
Thank you very much, Bruce. We have a couple minutes for questions. Is there any in the Zoom? No, I'm here. Yes, please.
Just a quick comment. There are actually many soil series defined as having arid soils with Great Plains.
Other
And in parts of the Midwest.
that shows you that's a measure of my ignorance.
And they're very useful for
Sure, absolutely. But are they the series are defined with buried soils within them?
Yeah, and there are other series where you can see a buried soil in the type description, even though it's not acknowledged by a B subscript.
Okay, excellent. So I take it back.
So to add to that though, it's only down to what, 60 inches. If you have buried soils deeper, if they're deeper than that, they're not going to be in the soil
Right.
description.
Right.
It's only within the upper, I can't remember off the top of my head, how many inches or centimeters.
Yeah. So how thick a deposit on the surface do you need before you consider that the soil underneath is buried?
It could be,
It's 20 centimeters.
It's 50 centimeter in soil example.
yeah, but
And also it could be between 30 and 50, depends on the thickness of the horizons.
See, from a geomorphic point of view, if I see sediment, I don't care how thick it is on top of the soil, that is an important piece of information, which is lost in terms of the way they classify the soils.
But the best thing is to look at the genetic horizon they describe.
Yeah.
If there's a suffix V, then you should be careful.
Right, no, but I mean, if they're saying that you need 20 centimeters or 30 centimeters of material to recognize it as buried, there's a lot of geomorphic information that is contained or that is lost in that by not recognizing.
Yeah.
Okay, sorry, I have
Yeah,
to stop
absolutely.
the discussion. You can discuss later. And now we have an online presentation by Goryachkin. Okay. Thank you. Then we will listen to the some analogues of late Paleozoic and Mesozoic soils.
Hello, dear colleagues. Can you see my presentation?
Yes.
Yes.
Okay. So I will speak about some analogues of some ancient soils in recent soil landscapes. So here just a picture of our history of the Earth, and you can see that most of the time there could not be soils like we experienced to do with. So I think that it is somewhere in Cambrian period only, just when we can see some plant with roots, because at the previous time there was just rootless organisms, and the formation of a soil was absolutely another way. So what about how can we try to understand, to get information, to find something about ancient soils which have the age of million of years, hundreds of millions of years. So there are some problems that we used to do with paleosols, mostly in Pleistocene. And as we saw from yesterday's presentation, a lot of paleosols of Pleistocene are available, and it is possible to study these soil bodies. And as for ancient soils, there are only very few findings of these real soil bodies. And mostly they are situated in very specific ecological niches when they can be saved in it's like river deltas, mangroves, swampy areas. So and this is very specific soils, and sometimes it's very difficult to imagine what kind of soils can exist on the watershed territories, not in these depressions and very specific niches. And also epigenetic changes of soil features which have an age of million years. It is mostly concerning recrystallization of neoformation and just extinctions of organic matter, and that's why we cannot use usual methods for studying these soils. However, we have some information from our colleagues from geology, and we could have information on lithology, topography, to some extent climatic conditions, mostly temperature, less with precipitation, and because of paleontological studies, we can have some information on biota. So usually paleosol helps to reconstruct paleo environment. It is especially for archaeologists and for paleogeographers. But now, if we are speaking about ancient soils with very old age, now it is time to formulate the reverse problem. How to model soil knowing soil forming factors. It is usual problem for soil geographer experienced in soil mapping, because we cannot dig everywhere, and that's why we just can understand the pattern of soil covers in just knowing, having knowledge about soil factors. So now I think that if we need to get some information or just imagination of soil of ancient epochs, so we need to use factorial pedogenic synthesis. So it is based on knowing soil forming factors and finding and analysis of recent analogues of ancient soils. And in sometimes we cannot do without simulation of ancient environment in laboratories. For example, low oxygen atmosphere we cannot find now in any place of Earth. So I will focus on calcareous material and gypsous material. They are highly weatherable, and they were very widespread during the Permian epoch and beginning of Mesozoic. So I will speak about this period. You can see that we have warm biospheres and cold biospheres, the presence of ice caps, for example, and at the end of Permian period, we can see some glaciation. So we could make a clue that this epoch was rather close to that we have now, and in moderate conditions, moderate climates. And Mesozoic is mostly warm biosphere without ice caps, and the climate was warm and mild. So these are the slide with this distribution of calcareous and gypsous material. You can see that especially calcareous materials are very widespread and is present in very different conditions, different climatic conditions, and then we can find analogues for these ancient epochs. So we have studied in the regions with different cryogenesis, from Central Europe and Northern European Russia to Baikal area in Siberia with very strong cryogenic processes. So let's begin with rather mild conditions. It is Phenoscandia, and we can see these calcareous materials, and mostly dissolution are predominant in these conditions, and the soils are consist of litter or erratic material, so morainic, lying on marble rock, and surface are cavernous and no layer of fine earth in soil profile. And just move to Baikal region. Sorry? Baikal region with strong cryogenesis. And these are this kind of soils. Mostly it is organic matter do not it's just mixed. It's not organic mineral complexes. It's mostly mixture of organic matter and fine earth. And you can see that we have about 50 centimeters of disintegrated material and with a marble powder at the surface. So here's this micromorphology. You can see just a mixture of calcareous material and organic matter. And just mostly prevailing of calcite, of course, with just a mixture of other minerals, but mostly you can see this just physical disintegration of this calcareous material. As for the soils on hard gypsum, so we begin with, in mild climate, it is southern Poland, and we can see that there is no cryogenic disintegration and no gypsum debris and powder. A sod is just lying on a cavernous gypsum rock. But absolutely another situation with some boreal soils on hard gypsum. We can see that there is very, very deep disintegration and some horizons with gypsum powder. And here's just the result of dry sieving. We can see that just the fine earth is mostly situated at the surface, but in some profiles we can see that is fine earth gypsum consisting of about 99% of gypsum without any silicates. And here you can see also micromorphological picture of this gypsum powder. And also another processes is forms of dissolution is also very typical for humid soil on hard gypsum. And here's this is some gypsum coatings on bottom of rock fragments. And so surely I cannot avoid just saying about white sands. It's close to your conference venue. But not only in form of sands. Gypsum exists in arid territories. Here's just another example of Mangishlak in Turkmenistan with very, very hard rock, also consisting only on calcium sulfate. So what are the processes in these soils with calcium matrix? So we have frost-affected disintegration, chemical dissolution, and also recrystallization, just shown as coatings at some places of gypsum and calcareous material. Yes, and just removal of calcium calcium compartments. So and total removal. And if you have, for example, hard gypsum with 99% of calcium sulfide, so you have 0 in the residuum. So, and here just the attempt to put all our soils in this diagram with mean here temperature, and also it's not precipitation, but coefficient of humidity. So it's precipitation for potential evapotranspiration. So, and we can see that there are some parts when we have only recrystallization, mostly disintegration and total dissolution. So, as for humid tropics, analogues of Mesozoic time, so this is the picture of karst of Madagascar, and unfortunately, I don't know, and I never met in the literature the information on soils on hard gypsum in humid tropics. I think that it is very, very unstable in such conditions. So, as for conclusion, so factorial pedogenic synthesis is proposed for modeling of ancient soils and soil landscape. It is based on knowledge on soil forming factors of the past and on the finding and analysis of recent analogues of ancient soils. Disintegration, mainly cryogenic one, is the most pronounced processes of the transformation of mineral mass of soils on hard gypsum and calcareous rock. Rock turns into regolith. This process, usually background one for most of the soils, is number one in processes for soils of calcium rock, calcium, calcareous and gypsum rock. Late Paleozoic is characterized by alteration of cold and warm biospheres when the disintegration may have prevailed. However, Mesozoic is characterized by warm conditions, and the dissolution of calcium matrix have been predominant. Thank you very much for your attention.
Thank you very much, Sergey, and we have time for questions. Is there anybody from Zoom who wants to do a question? No? So I have one question, and in Mexico, we have in the tropical area just soils with gypsum that we were very surprised to find because, as you said, the dissolution is very fast. But maybe this is because we have evaporites as parent material, and the waters are very enriched with calcium sulfate. So this precipitation during the dry season occurs, and then dissolution during the wet side, the wet season. So this is something that we have to take in mind for these past reconstructions, that even in the tropics, there is gypsum.
But
I don't know what is your opinion.
As I can imagine, it's not rainforests. It's yes, it is mostly semi-arid tropic.
Yes, it is around 3,000 millimeters of precipitation, so it is very wet. But the question that the situation is that we have dry season. The dry season is around January to March, and then from March, April to September, October, rain every day. So.
Thank you.
So any other question or comment? Yes, please.
Sergey, if we go back earlier than the Silurian, when land plants occupied the surface, and we go back into the Precambrian, presumably when there's only microbiotic crust or biocrust, still there was dissolution and reprecipitation occurring at the uppermost part of the land surface. Would you consider the fact that there could be Paleosol, Precambrian paleosols?
I hope that the answer should be at the presentation of Nikita Mergelov, who is a specialist in soil. It's maybe not just soil sensu stricto, it is like soil-like body, because these ancient bodies have some horizontalization because of microbiological activity, but they have no real soil horizon. So it is, I think it's soil-like bodies, or proto-soils, or soloids, it's different names.
Okay, thank you very much. And then we will move to the next presenter, that is Julia Konoplianikova, and she is going to talk about contemporary and paleofeatures in soils of South Siberia.
Yes, good day, dear colleagues. Do you see my presentation?
No, please share it, please.
Так, yes.
Yes, now we can see.
Yes, thank you. And I'm happy to represent you our work, recent and paleofeatures in soils of mountainous grey steppe landscapes, southeastern Altai. Surface soil profiles are generally interpreted and classified as containing features consistent with the actual environment. However, detailed hierarchical morphogenetic analysis gives us opportunity to identify paleofeatures in recent surface soils due to soil capability to record environmental conditions and pedogenic processes in stable elements of the soil body. And we studied profiles of xerophyte steppe soils on the southeastern Altai based on the hierarchical morphogenetic analysis with a special focus on soil micromorphology. Next. How to next. So our main method is hierarchical morphogenetic analysis. It's field morphology, and on the laboratory stage, it's meso, micro, and submicro morphological analysis. And also we use radiocarbon dating with accelerator mass spectrometry analysis. And our objects are situated in southeastern Altai. It's a mountainous area with extremely ultracontinental cryo-arid environment with permafrost here, and mean annual temperature is below zero. Mean annual precipitation is about 100-200 millimeters with summer maximum. And also we have here skeletic fluvial sediments and soils are very gravelly here. And we have 3 objects in Baguti River Basin, in Akhol Lake Basin, and in Chua River Basin. Our objects compose a landscape altitudinal sequence. The most humid object in Baguti River Basin is situated in 2,400 meters under Kryok-xerophyte steppe with alpine elements. And the central object is situated in Akhol Lake Basin in 2,230 meters under Kryok-xerophytic steppe. And the most arid object is situated in Chua River Basin under 1,900 meters under desertic Kryok-xerophyte steppe. And so we have here a skeletic Kashtanazon cambic in the most humid object, skeletic cambisol protocalcic in the central object, and skeletic cambic calcisol yermic in the most arid object. But all those soils are united within cryo-aridic soil type in the Russian soil classification. And all these soils have brownish A horizon, dull yellowish brown B W horizon. All of them have an accumulation of root felt between BW and BK horizon. And also they have a stony BK horizon with calcite and humus pendants on rock fragments. The main common features in studied soils are low decomposed fine plant residues in A horizon, clay silty coatings on mineral gray in B horizon, root felt between B and BK horizon, and calcite and humus pendants and silt cappings in BK horizon. The humus horizon is characterized by abundance of low decomposed plant residues, silty clay humus coatings on mineral grains and plant residues, and have a granular microstructure. In the most humid object, we have here also a big crumb aggregates and well-developed microgranules and a lot of plant residues. In the central object, we also have abundant, well-developed clay humic granules, low decomposed plant residues, and clay humic coatings on mineral grains. And in the most arid object, we have calcite coatings on grains in the humus horizon. Also, we have impregnation of plant residues by iron compounds and bicarbonates. And also we have here clay humic silty coatings on root residues. And the next B horizon is characterized by silty clay sandy coatings on mineral grades and rounded ooid aggregates. The most humid object is characterized by well-developed ooid aggregates, sometimes with inclusion of mineral grains. Also, we can see here granular microstructure and silty clay coatings on mineral grains, and the composition of this coating is silicate, so it is the same silty clay material as the main fine material of this horizon. On mineral grains, we have such coatings. And when we see the BK horizon in the most humid object, we also can see the rounded aggregates, sometimes they are cracked. The common feature of decay horizon is multilayered coatings on lower faces of grains and silty clay coatings on the upper faces of mineral grains. And in the most arid object, also we can see microcementations and total carbonate impregnation of the material. In the decay horizon, we have such types of carbonate features as calcified plant residues, pendants and their fragments, crack and fillings, calcified mineral grains, and impregnations. And para-extreme climatic conditions, ultracontinental cold dry climate, lead to specific cryogenic processes in dry conditions. So in these soils, we have abundant low decomposed fine plant residues, post-layering texture, frost-shattered aggregates, oid aggregates, and sandy silt cappings on rock fragments. And the central object is characterized by granular microstructure in humus horizon, silty clay coatings in dull yellowish brown B horizon, and calcite and humus coatings in BK horizon. But the most humid object has the most thick humus horizon with well-developed structure and mesofauna features. Cryogenic oid aggregates is better developed in this object, and post-layering texture also the most expressed in this the most humid object. And the most arid object is characterized by elements of desert parment. Also, it have a vesicular and laminated crust over humus horizon, and also it have carbonate cementations. So the following pedogenic processes well agree with current arid, semi-arid, and ultracontinental cold conditions. The first is accumulation of specific organic matter in A horizon. The second is biogenic microstructuring. The third is cryogenic processes like frost shattering, frost sorting, formation of silt cappings. And the next is recrystallization of calcite in pendants. And the fifth is impregnation of plant residues. And para-extreme lithological conditions, very stony substrates, up to 18% of coarse fragments, leads to localization of pedofeatures on the surface of rock fragments. So we have a lot of types of coating on rock fragments in the soil. They are silt cappings on the rock fragments, humus coatings, and three types of calcite coatings: loose micrite coating, dense micrite microsporite coatings, and dense sporite coatings. And what about composition of coating? Some of them composed by pure calcium carbonate. Humus coating have an organic matter with some impurities, and also in calcite coatings we have CO2 microlayers. Multilayered calcite and humus coatings on pebbles are the major block of soil memory in stony soils of arid and semi-arid regions. Each microlayer of multilayered coatings with different arrangement has recorded information about processes and environment of its formation, so we can reconstruct the history of the soil by sequence and morphology of each layer. We have dated humus and carbonate coatings, and we find out that humus coating were developed 3,400 Cal-BP years before present, and carbonate coatings were developed about 7 to 8,000 calibrated years before present. So calcite and humus coatings are paleofeatures in these soils. The typical sequence of microlayers in our soils is the first layer is dense sporite layer or dense macrite microsporite layer. The next layer is dense sporite layer. Then comes loose micrite layer impregnated by humus. So we can reconstruct the history by morphology and sequence of this layer. We can reconstruct the phases of soil evolution. These are formation of microsporite macritic dense silica-containing coatings due to short-term fluctuation of the shallow alkaline bicarbonate groundwater level in the semi-arid arid climate. The next phase is formation of sporitic dense coating under the slow accumulation of carbonates from low mineralized bicarbonate water in less arid condition. Then comes the alluvial formation of micritic loose coatings under stable aftermorphic semi-arid conditions. And then we had formation of humus coating in a cool, humid climate, alpha-humus phase of pedogenesis. And the next we have the alluvial formation of micritic loose coatings under the aridization of the last 1,000 years of Holocene. So cryogenic soils in Altai mountains are polygenetic. Their decay horizons contain relic features, evidences of former carbonates and humus migration in the soil, whereas upper horizon have features basically related to recent environment with cryogenic and biogenic soil processes. Thank you.
Thank you very much, Julia. Questions for Julia from, yes, please, again, you are live.
Thank you very much, Elizabeth. Of course, I cannot avoid asking question to this very interesting presentation, which has really great importance, not only for Holocene, also we have a lot of these cryogenic and cryo-arid features, especially in Pleistocene soils in vast periglacial areas of Eurasia and America. So this presentation is really very important for many of us. Julia, I have 2 questions. First, related to your micromorphological investigations of general soil mass. You showed us nice photos of granular structures, and as far as I understood, a part of these granular aggregates are of biogenic origin, they are coprolites, but some granular aggregates are of cryogenic origin. Since long time we have a problem how to discriminate granular, cryogenic, and biogenic structure. do you have some ideas, some criteria to discriminate them?
Cryogenic aggregates have a rounded shape, very cool rounded shape with a tiny clay, how to say, very tiny clay coating around this rounded aggregate. And our biogenic aggregates are not like a circle. They can be like crumbs or granules, but not like a circle in thin sections. But our aggregates are just a circle in and with clay around aggregate.
Yes, thank you. Very interesting. And my second question is related to this very nice carbonate laminated pendants which you have in your soils, and that are also present in other parts of the world, in Mexico also. They are laminated, and some layers are not only carbonate, but also with humus and even with iron, as you showed to us. I have a great doubt about your interpretation of iron humus coatings. You interpret it as the aluminium iron humus migration, something like a podzolic or spodic process. Am I right?
Yes.
Do you understand that for this you need a very strong leaching environment and to move pH of the soil well below 5?
Yes.
Do you suppose such grade of leaching at any time of Holocene evolution of your landscape?
Yes, we think that there was a humid phase with tundra landscapes, and when alphic humus immigration is possible.
And soil was completely leached? You don't have primary carbonates? Carbonate fragments in your soil?
Maybe pH was not so acid to leach all our coatings.
Well, I would propose you to consider an alternative version for these coatings, redoxymorphic processes. That's all.
Thank you. I'll think about it.
Can you please send your comments to Julia directly, because we have to move on.
I have no more comments.
Okay.
Thank you.
And then our next speaker is Shenggao, please. And now we move to China. And Sergey was telling me why people.
Good morning, ladies and gentlemen. I'm from Yang University of China. My name is Shenggao. My topic is later paleosoils, case study from tropical regions.
To the right. Yeah, both of them. Yeah, no, then the one on the opposite side.
Okay. This video is a sketch map of China. Then yellow color is loess, the red color is red paleosoils. As we know, many studies was performed on the loess, but
on the later paleosoil and later knowledge, limited knowledge, because a lot of information recorded as soil have lost under high temperature and high rainfall. Our research location is on here. It is Yunnan Guizhou Plain near the Qinghai Xizang Plain. This plain is located in the southeastern edge of the Tibetan Plain. It is called Red Palaeozoic because of the soil with darker red color. So we call it Red Palaeozoic. It's a typical landscape of the Red Palaeozoic, the darker red color. So our first objective is to understand the paleogenical processes of Red Palaeozoics. We collect the Red Palaeozoic profiles from 2,000 meter elevations. The thickness of soil generally has 3 to 5 meters. We take the soil samples at 10 centimeters in the field from the land surface down to the top of the parent layers. We use 4 technologies, including biological, geochemical, mineralogical, and local magnetic techniques. The second objective is to understand, to analyze the landscape erosion and tectonic uplift history of the plain embodied in the soil. First of all, I introduce the biological analysis. We measured soil pH, mensual organic carbon, particle composition. We find that soil have fairly strong acidity. The pH is from 4 to 5. The color is dark red color. The mensual height of 5 YR. So this soil is indicated the presence of hematite in the soil, which is characteristics of the tropical soil. The clay content is more than 15%. This figure is geochemical analysis. We measured the content of major and trace elements. Then we compare with the average composition of upper continental cluster UCC. We find that the soil have a much lower calcium and potassium content, much higher iron oxide. This is check content. The UCC normally cite abundance of major and trace element for the later paleosols as this case. Also, we collected some chemical, some recently introduced, such as chemical index of alternation, CIA. This figure shows us our soil compared with UCC and the European leader clay worldwide laws, just laws of East China and continentally related Earth. We find that CI of later paleosoils are in the range of 9.5 to 9.77. So this soil is have a much higher in CI index since UCC and laws and Europe leader clay and continentally leader earth. Generally, diagram is here is aluminum oxide, lithium oxide, potassium oxide. The little soil with is located in the Calinite and Jefferson site. It means this soil has intensive chemical whistling, indicate a strong chemical whistling, a chemical phenomenon for the Wang and humid region soils. This type of placenta molecular chemical whistling in indexes such as SA and SAF. The SA and SAF ratio of the little paleosoils range from 1.4 to 2.3 and from 0.8 to 1.7 respectively. These fields are similar to those found in the highly whistling oak soil and other soils. So these soils have much higher CI and lower ratios. Confirmed this the soils had experienced a much higher degree of whistling. Third, we use the X-ray to electron microscope to observe the police plane. The police plane have a number of deeper and interconnected delusion pits. This one, delusion pits on the surface of the place. These delusion features and glycos are commonly filled with iron oxide and clay. This kind of infilled place is common in tropical soils and is labeled as lunar place. This formation, the morphology and surface texture of the place planes are consistent with insert high degree of whistling of the soil pellet materials. The clay anxiety analysis. From the anxiety pattern, we can find that the little soil the mineral composition mainly include jepsite, hematite, granite. We also confirmed that the clay mineral is Jefferson and Calinite. In order to identify the iron oxide mineral in the soil, we continue perform the X-ray analysis. This one yes, the X-ray pattern of the clay. We can find the peaks of iron oxide hematite and mega hematite. Then we use DCP solution to remove the iron oxide from the clay. We can find that these peaks disappear in here, disappear. It means this mineral is oxide, iron oxide. As we know, magnetic susceptibility are commonly used to parameter change analysis in the Chinese losses. A lot of the data have published about the loss. We also use the local magnetic to measure the later soil. We can find our soil is much high than the modern soil. The index of later Paleozoic generally is more than 1,500 units. Generally, the modern soil is about several and 10 several unit. So the later Paleozoic is about one order of magnitude high than those for modern soil. High magnetic susceptibility indicated the process of hematite and mega hematite. We continue use the electron to identify the iron oxide. We find that this iron oxide is generally nanoparticle. The size is several nanometer in size. The scale is 5 nanometer. So this iron oxide about several nanometer in size. We measured the 4-section property of this soil. What a conclusion can we induce from the site of later Paleozoic? We can from the processes of later Paleozoics. The later Paleozoics have lower pH, about 4 to 5. High clay content, plenty of calinite and triplesite, and almost leaching of bases. High accumulation of lime oxide and iron oxide, and high degree of chemical visibility. The pathogenic characteristics are consociated with the localization processes in the other soil and the soils of the tropical soil. The existence of later Paleozoic is high altitude, about more than 2,000 meters, indicate an important process of indicator of tropical or subtropical environment. As we know, with the degree of weathering and soil development increases, the soil type is from the intersoil, incipient soil, alpha soil, thin edge soil, and ox soil. Our later Paleozoic is associated with the tropical paleogenic condition here. About the physical distribution pattern of soil in the normal condition of subtropical and tropical mountain, the soil distribution pattern is 6 to 800 above sea level is later later Earth. under 2,000 meters is yellow and thin in septile soil. But in the Palladian, it's in better pattern. The later paleosoils with located in the Polynesian surface of more than 2,000 meters. So it's inverted vertical contribution pattern in soil. The highly visibly the soil on the top of Palladian is contrasted with the normal distribution pattern. It means theta that tectonic uplift of Palladian change the soil physical distribution pattern. About the tectonic uplift. The uplift of Palladian occurred in the middle Pleistocene at about 0.8 million. The Palladian was lifted to current heat. The Polynesian surface of the Palladian with elevations of more than 2,000 meters is impossible to develop a highly resilient tropical soil. So it is deduced that little paleosols are formed at a high temperature and band rainfall condition in the early Pleistocene, and the same uplift to the current theta by tectonic uplift of the Palladian. According to the difference in elevation between the later paleosols and the modern later soil base, it is estimated that later paleosols have been uplifted about 1,600 to 2,000 meters since its formation. The later paleosols was uplifted to the Palladian Polynesian surface with an elevation of 2,000 meters. Which lead to the inverted vertical distribution pattern of soil in non-Palladian. This explains why the high visibly later paleosoils are widely distributed in the Palladian. We can see this method. Why? How to explain the later paleosoil on the top? After formation of early Pleistocene with high temperature and abundant rainfall, same other formation, the soil was uplifted more than 1,600 meters. Same on the top, this soil on the top of the Polynesian of the Palladian. This is why we find that the later paleosoils on the Palladian. It's possible causes. Thank you for your attention.
Thank you very much, and I will discuss with you during the coffee break because we have something similar in Mexico. But Nikita Mergelov, are you here? Can you hear me?
Yes, I'm here. Yes.
Yes, thank you. So can you please share your screen? I think
Sure.
Something a problem here in the room, but please share your screen.
Can you see it?
No, not yet. Just a minute, please.
Do you see it now?
No. No, we can see previous presentation.
Let me try the other way then.
I think this is not because of you. This is something I.
Yeah, but
Do you
we have his presentation for the keys.
Okay, yeah. And now, can you please share your screen? Yeah, thank you. Yeah, now we are
You see?
looking at the.
Oh, great.
Yours.
Great.
Yes.
So good morning, good afternoon, and good evening, everybody. You are in different places, and it's a real pleasure for me to participate in this conference in these times. Much appreciated. The reason for this presentation is that soil science should somehow address the rising knowledge on the ecosystems that existed in the early Precambrian on land, but outside pure aquatic environments. Here, when I say on land, I mean terrestrial environments, terragenous sediments, something outside aquatic environments, which aquatic environments, you know, they are very well trapping material and they provide the most of the paleontological data. And also there is a knowledge that the continental biosphere existed from the early Precambrian and was dominated by microbial mats. And there is some prominent evidence for these data. Also, we know that there were some oxidative weathering already before the great oxidation events, because there was a presence locally of some molecular or free oxygen. And also we have enhanced the concept of the extreme environment, the soil formation in extreme environments, and which can provide some real-time models to approximate formation of the earliest soils. And contemporary extreme environments, they can actually switch off some of the present soil forming factors like vascular plants, their root systems, and that's why they are very important. And we'll talk today about the proto-soils. This term is now beginning to be widely used when we reconstruct the early terrestrial biospheres and their soil covers formed under cryptogenic ground covers. And the proto-soils are used in two senses. First of all, it's just the initial forms of soil formation, and also these are the some beginning forms of soil formation in an evolutionary aspect. So there are data that oxidative weathering occurred before the great oxidation event. And we know this from the cerium isotopic anomalies, uranium, chromium, also from manganese retention. And there is a recent evidence from some very well-preserved and morphologically evident microbial mats from the 3.2 billion years siliciclastic sediments in Barberton in South Africa, Kapval Craton. And the oxidation could occur when the so-called oxygen oasis or whiffs of oxygen were present very locally. So we have the evidence from microbial mats, we have some evidence from paleosols, especially in phosphorus depletion, and we have some evidence from isotopic anomalies, that there was some oxygen locally and that there were microbial mats, and there was microbial life on land, not exactly in the aquatic settings. And today we are not talking about quite well-studied full-scale paleosoils. This is a wonderful example of the famous Waterval Onder paleosol in South Africa, studied by Gregory Ritelak. But we will focus on the initial stages of soil formations on rocks or clastic sediments. This is very hard to find in the geological record because they are often eroded, but we can use the principle of analogy to approximate these soils from the early Precambrian. And when we look at the modern extreme environments as proxies of Precambrial soils, there are basic 4 models of aquatic environments with amphibious, so subaqueous, subaerial regimes soils, because there were a lot of water and the continents were small. And of course, there were a lot of volcanic activity. So the hydrothermal proto-soils would be present at that time. And we have some fossil record of these 2. But if we want to imagine how soils looked when the soil formation just started to develop on rock surfaces or glacial surfaces, which were very glacial surfaces are very ancient as well. We know glaciers exist for at least 2.9 billions of years on Earth, of course, fluctuating. So the first 2 groups, I will just briefly go among them. The amphibious alluvial soils. This is the evidence from microbial mats in terragenous sediments. You see here not rounded clastic mineral fragments, which point us that it is terragenous material. It is draped by microbial mats. This is a wonderful work by Martin Hohmann, his dissertation and his publications. And we have also modern analogues of these. So modern analogues and fossil record from 3.2 GA Barberton. And these can be perceived as very tiny proto-soils under the microbial mats, which comprise giant sequences, multimeter sequences that are preserved in geological record. There's also work from the group of Van Kronendorp and his PhD student Djokic. She showed that in the famous Dresser formation, there are some geyserites that preserve microbial traces of microbial activity, very similar to the ones that we can observe in the contemporary volcanic hydrothermal settings. This is example from New Zealand. But what should we do with the rock surfaces when the pedogenesis started on it? We can use modern analogues from extreme environments, which show us that when there was no ozone layer, or it was just very weak, when the ultraviolet radiation was strong, and when the severe environments were present on the surface, the life can escape into the rock or the sediment and form continuous horizons underneath the day surface, because the light can penetrate through quartz or feldspar, and the primary production can occur inside the porous rock. And there are 2 basic profiles in modern endolithic proto-soils. Accumulative one with a continuous horizon of primary production, organic matter transformation. Of course, this organic matter and organisms interact with minerals and produce some microprofiles. And also we have kind of a alluvial differentiation with these bleached horizons, which likely was produced by fungi activity, the siderophores that transfer iron through the porous rock. And this evolutionary appeared on the later stages when fungi appeared on Earth. So this is a very nice example from the sandstone, Beacon sandstone in East Antarctica. This is photo from Henderson. And you see these iron accumulation horizon and the bleached horizon. And if you look at the chemistry of this profile, endolithic profile, you see some analogues of the E horizon, which is bleached and depleted in iron and organic matter. And you have 2 horizons which resemble BHS soil horizons of iron and carbon accumulation. The one is beneath, and the other one is on the top, because you have on the top an oxidation barrier where the iron also precipitates. And if you do some advanced analysis like nanoseams, scanning electron microscopy, microtomography, you will see that there is a lot of weathering processes that occur inside the endolithic profiles, and they are produced by mainly cyanobacteria and of course the associated microbial community. You can see this weathering halos around the cyanobacterial communities. You see the weathering front. You see the amorphization front in the primary minerals, which is produced by cyanobacterial biofilms. I will remember you that cyanobacteria can dramatically rise pH to 9 and 10 during photosynthesis, and then it can dissolve quartz, and then the pH drops to 5, 4, which can be conductive to the dissolution of feldspars. You have the pores inside with the organic matter accumulation. And of course, you have similar to soil processes of carbon stabilization. These are the clay minerals, and you have very close association of the green organic matter and red. These are aluminium and oxygen ions, which stand for the clay minerals. So the carbon is stabilized inside the endolithic profile on clay minerals. And if we look at the fossil record, the most ancient podzol is known from Carboniferous. But using the analogy from the modern extreme environments, we can actually, if we consider these tiny profiles of with bleached and horizon and iron accumulation horizon as proto-soils, we can extend deeper in the past the occurrence of alluvial differentiated profiles in the soil record. And indeed, this process leaves trace fossils that can be probably recognized in geological record. They can be destroyed by metamorphism, but in some cases they can be preserved. And you see this example from Antarctica, this bleached pattern. And the oldest known aeondolitic, that stands for the microbial boring cyanobacteria, which just bored some holes by dissoluting minerals, is known for 1.7, 1.5 billion years. But so we have a chance maybe at some time, if we look precisely at the geological record, to find some evidence for these endolithic proto-soils. And there is also some nice data coming from genomics, is showing that ancient bacterial lineages that exist in nowadays cryptoendolithic communities, they date back to 1 billion years. And these bacteria just now proliferate and spread and diversify in the contemporary Antarctica landscape. The hypolithic proto-soils are similar to endolithic, but they are these soils are formed in the clastic sediments. There's also continuous level horizon of carbon accumulation beneath the stone pavements, where microorganisms also escape from harsh environment on the surface. The cyanobacterial biofilms can lead to the production of aggregates and raise the content of carbon up to 1%. In the contemporary hypolithic proto-soils in East Antarctica. And there is some also evidence from hypolithic photosynthesis in the Archean, which produced locally oxygen in the hypolithic proto-soil, which then was just through runoff dissolved in the neighboring aquatic settings and causing the pyrite oxidation. So we, as soil scientists, can give some information to people who study ancient Archean ecosystems and the element cycle in that ecosystems. So the other environments that can help us to approximate the Precambrian proto-soils are the supraglacial zone. Those that existed on glaciers. Glaciers are very ancient. This is evident from diamectites of the Kapfel craton. So they existed on Earth as according to the nowadays models. There were never snowball Earth, but something like sludge bowl or sludge bowl Earth, and some areas of continents were exposed for free of ice, providing the fine Earth and the cells for airborne, for the distribution by air and sedimentation on the surface of glaciers. And contemporary superglacial zones, except for the Middle Antarctic or Greenland, they are never free of sediments. They always contain some dark matter. And the most famous one is the cryoconite. Cryoconite is biogenic aggregates formed by different organisms, but mainly by cyanobacteria. You see here a nice example from the fluorescence microscopy. You see the cryoconite granula that is formed on the surface of glacier in the melting holes, and it is covered completely by filamentous cyanobacteria. But actually, these cryoconite granules are much more complex. They are actually microecosystems with cyanobacteria, heterotrophic microorganisms, and a lot of minerals. You see the micromorphological image of cryoconite granula, and it's very complicated. You have this dark border and a lot of granules inside, primary minerals. And what is important, there is a lot of in situ production of humic-like substances on the surface and inside the granules through the heterotrophic transformation of organic matter produced through primary production by cyanobacteria. And this darkening causes and facilitates ablation of glaciers. But inside the granules, this is a microtomography image. We see a lot of pores. This is due to the decomposition of organic matter inside the granule. So we have the carbon accumulation and production on the surface, and we have also its degradation across the granula. And we have also very important component which resembles the soil aggregates, the presence of smectites or clay minerals. Here's the example from the Caucasus, and you see a lot of this green color stands for the smectites, and these are smectites which are distributed across these rounded granules. They interact actually with organic matter and stabilize the granula on the glacier environment. So if we look at the cryoconite granula, it's rather complex. We have the surface layer with clay minerals, with cyanobacteria, we have primary production, and we have the core with the composition and accumulation of residual products. We have, in some cases, when the granule is big, an aerobic zone, and this is really resembles the soil aggregates. Once ready deposited, it can contribute to the soil formation outside glaciers in the periglacial zone, or just on the other surface of glacier, and we see there a lot of decomposition and carbon dioxide emission. So this is one of the last slides. So if we imagine how could the early Precambrian landscape look like, we should consider not just only deep weathering profiles, deep paleosoils. We can consider some endolithic and hypolithic proto-soils which reacted to the harsh environment, mainly ultraviolet radiation on the surface. We can imagine, since Proterozoic at least, some soil-like aggregates on the surface of glaciers. And this process is very important when the Earth turned massively to a glacial surface. And of course, amphibian and also hydrothermal proto-soils we should consider. So if we come to the conclusion, the current situation with the knowledge in the paleoscience, paleoecology, paleontology, gives new opportunities to soil scientists to build models of ancient proto-soils, initial soils. And we consider here 4 basic models. The first one is cryptic proto-soil with endolithic and hypolithic hidden horizons underneath the surface. The amphibious proto-soils with subaerial and subaquatic regimes, which have evidence in fossil record, supraglacial proto-soils and soil-like aggregates, and of course hydrothermal proto-soils, which already also have some fossil record. And at the end, I would like to say that the ideas expressed in this presentation would not be possible without my colleagues. Thank you very much for attention.
Thanks a lot for this interesting presentation, Nikita. We have time for one very quick, short question, if possible. Is there any? I have seen some. Sergey. But you. No, sorry. Sergey, no, you, please.
Thank you.
You don't, Sergey, because you are not so quick.
Yeah, I just wondering if these so-called paleosols are now consolidated, and what was if there is any study considering this later consolidation.
Can you please repeat the question, because I hardly hear from the back side of the auditorium. Maybe you just repeat one more time.
Yeah, are these old Precambrian soils or so-called proto-soils? They are now lithic and consolidated, or they are just fine earth?
Are these Precambrian soils consolidated, or are they soft earth?
Oh, thank you. Now we're here. They are consolidated, of course, lithified and consolidated, because if you are talking about the fossil record, and if you are talking about modern analogues, if the interlithic protosols, they develop in the porous space of the hard rock. Hyperlithic protosoils develop in unconsolidated sediments. And but the fossils are always lithified.
Okay, thank you. Thank you very much, Nikita. And we have to move to the next presentation by Bea Menendez. And she's going to talk about varnish desert in Mexico in relation to archaeology. Please share your screen.
Good morning. Can you see the presentation?
No, please share your screen. Yeah, now it is. Thank you.
Okay, thank you. Thank you very much to the organization of symposium and this session. It's a pleasure to be here today with this communication about desert varnish in Mexico, in northern Mexico. Well, what is desert varnish? It's a thin micrometric layer that coats various lithologies, predominantly in arid zones and desert environments. It's composed of approximately 70% clay minerals and 30% iron and manganese oxides. Its color range from black to reddish. It has an extremely strong, slow growth rate ranging from 1 to 40 micrometers per 1,000 years, reaching thickness of 200 micrometers. Its slow and gradual formation suggests that this desert varnish has a surface structure formed predominantly by past environmental factors. Well, the desert varnish has a cultural value. Since human groups around the world have used it since prehistoric times as a canvas for engravings. And what are petroglyphs? Is one of the forms in which we find rock art. Petroglyphs are found on exempt rocks or on walls in the open air. They predominate in desert environments, since painting is less well preserved. They consist of making an image by means of subtractive techniques. That is so to say, removing part of the surface of a rock. They are made using various techniques, such as incision, pecking, carving, or abrasion, or even a combination of several of them. When engravings on the rocks, the internal part is exposed and it's groove where the varnish is formed again. The desert varnish was formed under specific climatic conditions. Because of its gradual formation, numerous studies suggested that desert varnish represents a surface structure predominantly formed by environmental factors over time. This is considered a paleopedogenetic characteristic. In addition, it has other components such as certain rare elements on air, dust, and aerosol that are deposited on the rocks from the atmosphere. An important aspect about this desert varnish is that it has been used to reconstruct the paleoclimate of landscapes in desert environments. It is known that, for example, humidity is also a factor that influences and accelerates its formation. In short, it can be said that local and regional changes in dust, climatic fluctuations, erosion, and sedimentation processes could be reflected by desert varnish components. Therefore, this paleoclimatic reconstruction can be observed and established. Rock art is distributed over all continents, except for the poles, which are covered by ice, and it's not possible to identify rock art here. The varnish are also distributed in points marked in the image. They are found in all continents. And in this image, we can see different engravings elaborated on rock that present different variation of varnishes. Desert varnish is the varnish that provides the most data on its formation process. However, varnishes are found in other types of environment. As we see in the image of Canada here, which has more temperate and humid environment. The study area is marked on the map with the red circle. The region is framed within the Sonora Desert. It's the area of La Proveedora and El Arroyo de las Flechas. La Proveedora is located just a few miles from the city of Caborca within the Puerto Blanco Range. It's part of the series of hills that are divided into La Cueva Hill, La Proveedora, and San Jose or La Calera. La Proveedora is formed by hundreds of rocks with engravings. Another site, about 10 miles, more or less, from La Proveedora towards the coast is the Sierra del Álamo. In the surrounding of this mountain range, there are several locations with petroglyphs, but with less concentration than in El Arroyo de las Flechas. It should be noted that, unlike La Proveedora, El Arroyo de las Flechas is a large panel in a rocky front that is located in the bed of a stream. In the northern region of Mexico, specifically within the Sonora Desert, samples were collected from La Proveedora and El Arroyo de las Flechas archaeological sites and subjected to various analytical techniques to obtain information about the nature of desert varnish. The different samples collected were obtained from the surrounding of the petroglyphs. Non-anthropized rocks were selected but to the samples, no? And that contain a very marked desert varnish accumulation. As we can see in the image, the rock types are different, even though the locations are not very far from each other. The nature of the La Proveedora is granitic, while El Arroyo de las Flechas is a sedimentary, specifically sandstone. A set of analytical techniques were applied to these samples to determine their mineralogical, chemical, organic, and biological composition. Well, its analysis were applied to the transversal section of the desert varnish. This analysis revealed interesting results regarding the content and distribution in the varnish. As can see in the sample of the image of La Proveedora, on the left side, the desert varnish microlayers are observed on the parental rock. In the upper alt, some botryoidal structures are observed. The image on the right is the same, but mapping the elemental composition. Varnish is iron in red, manganese in green, and the contact with the parental rocks is blue, potassium in blue. Potassium. In the case of El Arroyo de las Flechas, the elements are salt, iron, and manganese. In the same from El Arroyo de las Flechas, spores and clusters of bacterial structures were also observed embedded in space and pores on surface of the varnish. XRD analysis allowed us to see the composition of the different elements in the samples and parental rocks. As an example, we have in the image this graph of La Proveedora. It shows two different layers of desert varnish and the analysis of the main minerals. A large amount of potassium and plagioclase, and to the lesser extent quartz and pyrrhotite are observed. In El Arroyo de las Flechas, minerals such as quartz and andesite, among others, predominate, which is characteristic of the rocks in the area. In the analysis carried out on the varnish, a large proportion of quartz and to a lesser extent pyrrhotite were observed. In general, the varnishes observed do not present a well-defined internal structure, although some incipient patterns are observed. In sample for El Arroyo de las Flechas, some dome-like structure appears. It's difficult to define since they do not show an internal structure, or the dome-like structure is due to an incipient botryoidal shade of the manganese oxides. In the case of La Proveedora, a well-defined botryoidal shape of a manganese oxides is possible. The results show that there is no relationship between the mineralogy of the rock and the chemical composition of the varnish. In this sense, it is evident that the morphology of the varnish is not affected by the mineral composition of the rock. This suggests that the origin and composition of the varnish come from allochthonous sources, such as Aeolian sources, in combination with physical methodological phenomena, temperature, radiation, humidity, and biological activity. However, depending on the type of the rock and mineral closest to the varnish might or might not penetrate to the rock. Well, the archaeological sites. La Proveedora presents a large concentration of petroglyphs. More than 5,000 engravings have been counted between different mountain ranges. In the image above, we can see some types of representation, such as anthropomorphic, geometric, which are always the most represented, and animals. There are also astral symbols and elements known as labyrinths. It's considered that chronological it's part of the trincheras tradition culture due to archaeological elements such as projectile points, lithic fragments, smooth ceramics, decorated trench ceramics, terraces, and shell objects, among others. However, also this evidence exists. The archaeological record gives reference to a human occupation in La Proveedora that could be dated back to the Middle Holocene. This is evidenced by the remains in the archaeological context of lithic industry associated with projectile points from Pinto, San Pedro, and Ciénaga faces. The Arroyo de las Flechas is a rock located on the margin of the stream, and therefore no associated archaeological material is preserved. The set presenta around 800 graphic units, and all recorded units are engraved except for the remains of painted figure. It has been observed that the groove of the engravings shows different degrees of patellation. This will indicate that the engravings were made in different stages, as is the case of La Proveedora. As for the typology, it is very broad, as we can see in the image below, and it contains geometric figurines, human, anthropomorphic figurines, astral symbols, and among the instruments are the rounds that give the site its name. They have been compared with lithic typologies. They have being compared with lithic typologies from the other place, since we don't have diagnostic archaeological materials. As in La Proveedora, the engravings are round, date us back to periods of occupation older than the trincheras culture, tradition trincheras culture. Well, and finally, at the paleopedogenesis level, we can say that desert varnish can be considered an indicator of past environments. From the analysis carried out on this varnish, they indicate that in older times, a more humid environments and less extreme conditions prevailed in Sonora. They are indicators of past atmospheric composition and therefore paleoclimatic indicators. Finally, at the paleopedogenesis level, it should also be noted that ancient microorganisms have been preserved within this desert varnish. At the cultural level, the desert varnish serves a natural canvas for a rock art, mainly in these desert environments. In addition, from the analysis of this formation, it helps to adjust the temporality of human groups that create these representations. Therefore, the patina can be considered a micro-paleosol, a related phenomenon formed mainly in the terminal Pleistocene in Sonora. Therefore, we can understand the desert varnish and its formation by study and analyzing the petroglyphs. Thank you very much.
Thank you, Bea. We have time for questions. If there is somebody who wants to ask from Zoom, nobody? No? Then I will ask something about the alloctonous material that you have told us. What is the source? This is from the neighbor soils or from the distance?
The same is near the petroglyphs. No, the petroglyphs, but near here, the site, because the conditions there are similar.
Okay, thank you. So with this, we close this session, and then we have the coffee break. Maybe we can short.
Yeah, because people already asking if we are going according the schedule or later. Yeah, so I'll answer that we are trying to go follow the schedule. Okay.
10 minutes for coffee break?
Yeah.
So 10 minutes. In 10 minutes, we
Спасибо. Can we start? Are you ready? Yes, more or less. Okay. I hope we are ready to start the next session, and we can plan a set of interesting presentations. So please remember the rules did not change. So we have 15 minutes for presentation and time for additional questions. So as first, Ksenia Bakhmatova. Yes, are you ready, Ksenia? Are you with us?
Anastasia Shishukova, Softa, and I'm ready.
Okay. So please start your presentation.
Can you see my presentation?
Yes.
It's okay. Good evening. Good day. I'm very glad to present you our report. This report is a result of joint work of archaeologists and soil scientists, and the work is devoted to the study of urban soils in the central part of St. Petersburg. Despite the young age of the city, this year it turned 3,020 years old, the central part of the city has changed significantly from the moment when the city was found to the present days. The aim of this work to study the properties of urban soils of St. Petersburg as a reflection of the city history. St. Petersburg is located on the northwestern region of Russia and was founded by Peter I, and St. Petersburg is the youngest northern megapolis in Europe. In this report, the soils of Rumentsov Garden was selected as for objects of interest to us. The garden is located in the central part of St. Petersburg on Vasilievsky Island. The history of formation of St. Petersburg and Vasilyevsky Island are closely connected. This is a map of area before the foundation of St. Petersburg, and the city was founded on the delta of Neva River. In the 17th century, it was a swampy, waterlogged area covered with sample trees, spage, beech, elder, ashen. In the future, the territory of island was dried. The island territory was drained during the early stages of city development. Soon after the foundation of St. Petersburg in 1703, Vasilyevsky Island was practically inhabited. Perhaps it was due to the fact that during floods, the water covered it almost completely. The development of territory began after 17th century, when Peter the Great had a plan to create a city of the island similar to European cities. A network of parallel prospects and intersecting streets was planned, which became the basis for future development. By the map of 1744 here, we can see that stone houses were built on the island and part of island were used for agriculture. At the beginning of 18th century, the site of future garden was occupied by Menshikovsky market. Later, during the nearby construction of Academy of Arts, building materials were stored here. The parade ground of Cadet Corps was situated at the place at the end to the 19th century. On the map of 1893, you can see the location of Rumyantsev Garden and of Rumyantsev Obelisk. On this map, here is Rumyantsev Garden, and in 1927, the layout of the garden was changed towards simplification. And now the total area of garden near 1 hectare and total of 220 trees. Koak, Linden, ash, maple, and larch grows in the garden. 2 soil profiles were chosen in archaeological excavation in the trench crossing the garden from the center to the eastern border. One profile, profile 2, was situated in the central part, and another profile, profile 3, was situated in the eastern part of the garden. The soils were named as Urbostratesium according Russian classification and Urbic Technosoils according to WRB. The schematic construction you can see on a picture. The archaeologists found that culture layers in the garden have a thickness about 2 meters and with reaching from central part to the periphery. This indicates the structure of the initial relief of the site where the central evolution elevation was surrounded by swampy depressions. The buried humus glaze soil was found here from 1 meter 17 centimeters. Methods and facilities you can see on this slide. It is standard methodics. The initial soil forming material is of the soils is presented by late alluvial marine Littorina sandy loam. The sediments were called the Liparine deposits because it was found by the Littorina Sea, the predictor of modern Baltic Sea. The deposits are late and characterized by domination of sandy and silt fractions. Soils have sandy and sandy loams texture And this makes it possible to assume that local material was used for the formation of the bulk culture layers for both profiles. The content of organic carbon in soil horizons varies widely, and it depends from the genesis of the material of the culture layers. In second profile, 2 peaks of organic carbon content were found in the organic horizon of the buried soils and in the upper horizon of the modern soil. In the third profile, the content of organic carbon is individual for each layer. Along all profile, soil have an alkaline or near the nature reaction. Soil profiles supplied with mobile forms of phosphorus. Soil forming material contain low concentrations of heavy metals against culture layers, which contain high concentrations of heavy metals. Of course, the main role is played character of anthropogenic impact during the formation of culture layers. Layers with a high content of heavy metals are confined to the time of reconstruction of building located near the garden and communications located in the garden itself. Here you can see the similar regulations. Micro-artifacts were studied in our soils, artifacts from size 1 to 0.25 millimeters. We divided artifacts into 2 groups, natural artifacts and anthropogenic artifacts. Natural artifacts represented by quartz, feldspar, and biotite. Anthropogenic artifacts represented by fragments of bricks, ceramics, glass, pieces of lime, slag, construction, garbage, mortar. The particles with particles is situated in the central part of the profile, and nature particles we see in the upper horizons of profile. At the bottom part of the soil profile, we find artifacts, charcoal, timber fragments, bone, glasses. Using a desktop scanning electron microscope, we analyzed the chemical composition of artifacts in order to understand what elements, including to soil material during weathering of artifacts. Mortar, ceramics fragments, and as a conclusion, we can say that urbostratesiomes and urbic technosoils dominate in the historical center of St. Petersburg. The original nature soils can be found under culture layers with a total thickness near 2 meters. The urbostratesiomes often contained a significant amount of artifacts, mainly represented by construction debris. The composition, quantity, and size of anthropogenic inclusions depend on the history of the site. The soils of the historical center have predominantly alkaline reaction, contain carbonates, and an increased content of mobile phosphorus compounds. The content of all list components varies considerably along the profile. The profile of urban soils reflects not only modern soil formation process, but also the history of land use. Heavy metals content along the profile depends on the history of land use. Buried nature soils and natural parent materials are characterized by a minimum content of heavy metals. Thank you for your attention.
If not, so maybe I will ask first question. Do you have any idea to explain, how to explain the spectacularly high content of lead in some layers of these anthropogenic soils up to 500 ppm? So it is extremely high. Why?
We think it may be possible with reconstruction of this territory. Building.
You showed us that there is. Okay.
I don't hear.
You showed us that there is glass. Glass, maybe it is a question of kind of the glass, because we know sometimes for preparation of crystal glass, a lot volumes, amounts of lead were used. So maybe it is connected also with glass production if it was produced in this area. Yes. And the other remark I have, because you showed us that, okay, it is just first remark, but you don't agree. It is up to you. But I've seen this slide only for 1 or 2 seconds, so I'm not sure, but you told us that the buried soil, original soil was ambric clay soil, but pH you showed us about above 7 for these for the layers below 160 centimeters. So maybe it is not ambric, maybe molic. We should check it, I think. Well, it is only remark, only remark just to check it, because ambric horizon for such alluvial soils are not so common. Alluvial soils typically are much more fertile, eutrophic, and we rather expect rather molic horizons there. But as I told you, the data I've seen it only for seconds, so 1 second, so impossible to conclude this. Okay, maybe other questions. If not, so thank you very much. Thank you for presentation. Interesting material, and we can invite next person, and the next is Alena Svechkova. Alena, are you with us?
I'm sorry, I'm Olga Khakhlova.
Olga, we have many changes. Okay, Olga.
No, not changes. May I ask you to move the Alena presentation some later, 1 or 2 presentation later? Is it possible?
Maybe it is. The next person which we have in our agenda is Daria Mikhailova. Is Daria ready to start?
Yes.
Daria?
Yes, I'm here. Just a few seconds.
Okay, so please start with your presentation. The next person is Maxim Bobrovsky. I can see Maxim is also with us, so we will continue. Okay. We can see your presentation, so please start. Do you hear us? We cannot hear you. Maybe there is a problem with your microphone.
And now?
Now, yes, it's okay.
Okay, let's start again.
Okay.
good day, everyone. Tomorrow, I'm presenting the report, Soils of Kugan Cemetery, indicating the paleo environment in the forest steppe area of the Central Russia upland at the turn of millennia. Our research aims to describe the variability of surface and buried soils properties to reconstruct the paleo environments of the area based on these properties, and in addition to explore technological specifics of the earthen constructions of this cemetery. The study site is located in Lipetsk region of Russia, in the forest steppe zone. The cemetery includes over 100 of objects and is located in the forest surrounded by arable lands. We explored two buried soils, buried under a kurgan and under a rampart of the burial ground, of ritual ground, and 5 surface soils to exclude the influence of special, to ensure that we are discovering the environmental changes, not the special variability of soil properties. Both buried and surface soils were described as grazomic luvic phaeosomes. According to radiocarbon and archaeological data, soils were buried in the 3rd century AD. Here in the lower picture, you can see the rampart of the burial of the ritual ground under which we described soils, and also we described buried soils under kurgan of a complex structure. The kurgan includes the earthen brickwork in the central part with contrastly visible lights and dark bands of it, and the earthen mound over it, and the total thickness of the construction is around 70 or 80 centimeters. The top of the paleosol and the end of the burial mound is marked by a thin layer of charcoal from some campfire which were here during the construction of the kurgan. Both buried and surface soil are silt loam or clay loam in the textural BT horizons. In the lower part of buried soil 1 and surface soil 4, we can see the increase of portions of sand and the change of the textural class to sandy clay loam, which is marking the change of the initial deposits there. But buried and surface soil has, in general, close particle size distribution composition. All soils are described soils are slightly acidic, but we can see that pH of the buried soils is slightly more alkaline than of the surface soils. It's about 0.3, 0.5 higher, and the exchangeable acidity in the buried soils is lower than in the surface ones. The total organic carbon content of buried and surface soils is close, but taking into account the temps of biodegradation of organic matter in the buried soils, we can calculate the initial organic carbon content according to methods of described by Ivanov et al. And if we calculate the initial total organic carbon in the upper parts of buried horizons of buried soils, we can see it's about 0.7 to 1.4 higher than in the surface in the modern surface soils. Also, in the buried soils are more clearly visible and more dark humus coatings at the edges of the pores than in the surface soils. Iron fractions in the content of iron fractions in the buried soils is low but higher than in the surface one, mostly due to crystalline forms of iron, whilst the active forms are close in both of them. If we see palynological spectrums of buried and surface soil, we can see such differences as in the arboreal spectrums of surface soil is more diverse and includes more includes less thin-leaved species and more species such as oaks, elms, and maples, whilst in the buried soils the forest, the trees were less diverse and consist of from thin-leaf species such as birch. In the grasses, we can see that nowadays there are significant amount of pollen of sedges and cattails, which are not seen in the buried soil assemblage. In the phytolith complexes of the buried soil, we can see the quite high portion of reeds, sedges, and mosses, which is marking which are phytoliths associated with the cultural layers with on which the tribes habited for some elongated time. Also, in the earthen brickwork of the kurgan, which contained lights and dark stripes and bands, we can see differences in both of these light and dark bricks. Light parts contain phytoliths of reeds and sedges, and in the dark part there are none of them. Also, but the dark part includes a highly developed photonic complex, which is not observed in not any horizon of buried or surface soils. Cutons like this are presented only in the dark bricks, and they are highly organized. So we presume that the material was compacted while constructing, and probably watered with river water, which resulted in the appearance of reeds and bulrushes and sedges in the phytoliths, and compaction resulted in this cutonic complex. So to conclude, we can see that paleosoils compared to the modern ones are more alkaline, contain more organic matter and crystalline forms of iron oxides, are visually darker and have visually darker cutants than the modern ones. But all these differences are small, and they didn't result in classification distinctions of the soils. Microbiomorphic assemblages shows that forest vegetation in the past was less diverse and less mature, with more portion of invasive species, and both soil and biological evidences allows us to assume that the environment was in general similar to the modern one, but slightly more arid than modern climatic conditions. And the brickwork material was made using a complicated technique, was mixed and compressed. And the ancient peoples used some light-colored material, which they added to this to create light bands of the brickwork. Thank you for your attention.
Thank you very much for your short but interesting presentation. So we have time for questions. Yes, please.
Yeah, thank you, Dario, for your presentation. I have a few questions and comments. First of all, you haven't shown us any contemporary information about the environment, about contemporary environment. It is in such conditions is very complicated to discuss about the reconstructions when we don't know where your burial mound is situated, located in such region, in what region, climate and vegetation and geomorphology and all that. This is the comment. And the point, I would hardly agree that river water could give you flatlands of sages and reeds. It sounds pretty suspicious, actually. And the question is about the pH. Do you believe that pH was preserved as it was through the thousands of years? That's the question.
Thank you for your comments. About the river water and phytoliths, it's really very suspicious, and we it's really suspicious, and we are not quite sure how exactly they used that and did this thing, because it's strange that they appears in the light parts and do not appears in the dark parts, whilst they're really closely mixed with each other. And about the pH, I don't think that about the pH, could you please repeat the second part of your question, because I didn't hear it quite well. But from what I can say now, they are
pH could stay. Excuse me. Excuse me. No.
Could what?
No. Okay. Do you believe that pH ratio is the same as it was during?
No, of course not, because it's
in the past.
No, pH is not like it was in the past, because it's very very quite quickly changeable
yes.
Quite quickly changeable property. But nevertheless, in both of them, it's in both of bird, it's slightly but higher. So it's what we observe.
But you cannot base your reconstructions on such a flexible parameter. Thank you.
Okay. So I am surprised. Just a comment that you found and in Poland. So we looked several times in soils, and typically we have only single grains. So I am surprised that you found in buried soil so rich material just to reconstruct the vegetation in such soils. But it's just my comment. I am surprised also that maybe the pictures were not so good, but typically in this burial material, this mold material, if we can observe the clay cutans, they are clearly stratified with several strata due to disruption. How to say, discontinuities of the material, and we showed us beautifully clay cutans, beautiful clay cutans without stratification. Are they stratified the cutans or not in the mold?
Sorry, could you repeat the second part? Are we stratified in what? I can't hear you quite well.
Okay, maybe we don't.
Actually, it's very interesting question. Yeah.
Yes, according to the picture, because as I understood, the pictures refer to the mold, not to the buried soil, but to the mold. Yes.
To the bricks, I guess.
It's the bricks. It's the dark part of the bricks, and these cutans are probably artificial because we can see such well organized only in the bricks, not in buried surface.
Yeah, it seems like it's a suggestion.
Because where were the bricks? I didn't see them in the.
Yeah, me too.
Which bricks did they put bodies, and then they were like a brick made of the bricks, and then the soil?
I guess it wasn't there, but shall we ask the presenter?
Because we are not finally sure which culture is it and what time, which culture.
In the same question.
In fact, many information are missing. Okay. So, do we have more questions?
About the bricks, where they are, the bricks.
Yes, the bricks are in the core part of the kurgan. They cover the burial and the dead body itself. It's about 40-50 centimeters of the brickwork, and it's quite small in the diameter. It's about 2 meters, whilst the kurgan is about 12 meters in diameter, and they are covering the most significant part of the burial. So they look like this, and it's late Sarmatian culture of the early Iron Age, which built this.
Okay, we are waiting for publication for more extensive paper with picture explanations, climate also, yes, vegetation, yes. So we will analyze in details your finding. For the moment, thank you very much for your presentation.
Thank you.
Stay with us. And now a question to Alena Szymczak. Are you ready maybe now, or next person should I ask? Maybe. Not yet. Okay, so maybe now Maxim Bobrowski. Maxim.
Hello.
Are you with us? Yes. Are you ready?
Hello.
Can you start with your presentation? Okay.
Do you see presentation?
Yes.
Just a moment.
Okay. Slideshow, please.
Yeah.
You can change the slideshow. Yes.
It's okay. 4 years ago, we present results of our work for this territory. It was only 3 hill forts. for this time, we found new hill forests for territory, and the aim of our research to study cultural layers of certain early Iron Age hill forts for different composition and chemical composition, charcoal concentration, taxonomic composition, and stratigraphy. Our study area, it's Penovsky district of Tver region. It's Valdai upland, upper reach of the Volga River. It's a hemiboreal forest region with dominating hilly plain and with Pinus sylvestris and Pizza abies forest. Background soils are albic and antic podzols. In this slide, you can see map of hill forests in the upper Volga and western Двина rivers. Excuse me for Cyrillic in the map. And red is our object, brown it's other hill forests on territory, and green it's just 4 hill forests investigated by its stationary excavation. It's list of our objects, certain hill forests, and this photo for few hill forests. Only 3 hill forests presented now by meadow vegetation, but others now is forest with pine or spruce dominating. Hill forests located on local elevation, most of them in promotion zone Murray Hills, and you can see a LiDAR map for 3 hill forests. Methods, we study cultural layer, description and sampling. Soil samples were taken from the area of certain hill forests using soil drill. We used pedoanthropological methods as determination of charcoal concentration and taxonomic identification of charcoals. We used radiocarbon dating for 92 samples and analysis of physical chemical properties of cultural layers and soils. It's examples course from some hill forests at the boundary of dark cultural layer at bedrock. And this scheme of thickness of cultural layers, you can see very different parameters as coloration and the thickness. Coloration is brown, dark gray up to black, and dark coloration is determined by high content and dispersion charcoal. And the thickness of the dark culture layer varies considerably both between and within hill forests, from 30 for more than 1 meters. Sand fraction absolutely predominates at the paleosoils of all hill forests. Its specific structure, excuse me, just a moment. It provides high water concluding capacity and significant aeration of all strata. Some features of the culture layers of the hill fort. Culture layer is represented by dark sand, saturated with charcoals. It's homogeneous without interlayers in most hill. Culture layer is on the surface, not buried, and most of the hill forests have a single homogeneous culture layer, except atoll hill forests. Parameters of culture layers on the hill forests allow us to attribute them anthrasols, pedourbaniziomes, and more to archaeological dark earth. At the same time, they are surface paleosols. At this slide, you can see average concentration of charcoal for all hill forts, and it's not high concentration. In soil around hill forts, we can see more high concentration of charcoal. These we present probabilities of calibrated dates for charcoal from culture layers of studied hill forests. And we can see that oldest dates of the 13th century BC found for 4 hill forests, and the mild period of human activity 2 centuries before it, 2 centuries after Christmas.
No.
Share your slide again, please.
Okay.
Maxim, we lost connection for a while with you. Do you hear us?
It's not.
Excuse me, very bad signal.
Yes, we also lost connection.
Yeah, at this slide, you can see taxonomic composition of charcoals with dominating of coniferous species, pine and spruce. And diversity of tree taxa in the local area is high for the southern taiga region. As pine forest with relatively poor species composition now dominates the area. And this is a reconstruction of species composition for different time. And we can see that the highest tree species richness was recorded as the early Iron Age. In this time was presented Ulmus, Quercus, Corylus, and other broadleaf species. It's example of some parameters chemical composition, and you can see the carbon concentration reach 6-8% with is 3 to 4 times higher than background soils, and nitrogen concentration exceed background concentration up to 7 times. And this table for element concentration. And we can see that 6 elements were found only in paleosoils, and concentration other 6 elements were higher in paleosoils. And conclusion that archaeological dark cores presented at all culture layers on the certain studied hill forests. Most of the hill forests have single homogeneous culture layer. The thickness of dark culture layer runs from 30 to up to 1 meter. The main period of human activity in the forest went from 2 century before Christmas to 2nd century after Christmas. And taxonomic composition of the chakra from the hill forest was represented by 17 genera of woody plants, including all 3 species currently growing in the upper Volga region. And very high concentration of some chemical elements were found in the culture layers compared to the background soils, as well as unique elements not found in the background soils. And thank you for your attention. Excuse me for bad signal.
Thank you very much. Thank you very much. We have time for questions. Yes, please ask. Yes, please.
Why did tree species diversity decline through time?
Can you answer?
Excuse me.
Надо сюда говорить.
Yeah, it's good. Yeah.
Why did the diversity of tree species decline through time since the Iron Age?
No.
Did they select trees, or is it some climatic driver?
All species we can see now in this territory, but in around these hill forests we can't see these species, but in the region this species present.
So it's not declined.
There is a question.
Yes, there is a question from Olga. Please, Olga, ask your question.
may I ask you about environmental reconstruction? Do you have some information studying 13 Iron Age hill forts about paleo-environment in that time? Thank you.
Yes, we have reconstruction by palynological data for 2 books, and it was an article by Yuri Mazey and Taza, and for this time environmental condition was close to today. Yeah, to sorry.
But do you think that the higher contribution of spruce could indicate more moisture climate or maybe higher groundwater table compared to today? Maxime?
No way.
But we lost or?
No, it's here.
Okay.
Maybe.
So probably we cannot continue discussion. So thank you very much if you can hear us. If not, also thank you very much. So now we will check the next presenting person. It is Tanya Garcia. Tanya, are you with us?
Yes, I'm here.
Yes. Can you start with your presentation?
Yes.
Okay, so please.
One
open it.
He was supposed to be here.
Okay. Okay. If you can switch to the slideshow. Oh, yes. Okay.
Okay. Yes. Okay. Good afternoon. My name is Tania Garcia, and I am part of the Paleosuelos group of the Institute of Geology of the Autonomous University of Mexico City. I'm going to present this work to you, which is part of the investigation of one of the sites that I study in the PhD. This site is the Templo Mayor of Tenochtitlan, and these works called Indicators of Anthropization and Natural Events in the Landfills of Templo Mayor, Mexico. The lake landscape of the Mexico Basin was one of the most important factors for the development of the different populations that occupy central Mexico during the pre-Hispanic era. The Great Lake of Texcoco provide resource for feeding the population, navigation, and materials that allowed the construction of temples, buildings, and platforms. The edaphic materials at the bottom of the lake, and in certain cases, the soils of its shores, have served to understand the environmental characteristics at the time of occupation of the site. That is why for this research, the study and analysis of the fields are the key element to understand more the archaeological site. Different studies have demonstrated that anthropogenic events modify and alter the natural pedogenetic trends, and these modifications are recorded in the archaeological materials. Templo Mayor was the main ceremonial center of the Mexicas, the main culture in central Mexico. The temple consists of 7 construction stages, as we can see in this image. Each stage corresponds to an expansion of the temple. At the top, we were two buildings in this part that painted red and blue and dedicated to Huitzilopochtli, god of the war, and Tlaloc, god of the rain. This site was occupied mainly by the late post-glacial period from 1325 to 1525 with the arrival of the Spanish. Since the first excavations of the archaeological site, hundreds of elements such as precious stones, ceramics, animal bones, and large monoliths like the Coyolxauhqui and the Tlaltecutli have been recovered. For this reason, in collaboration with the Templo Mayor project led by archaeologist Leonardo López Luján, in 2016, a first approach was made with the soils of the site, and after a new sequence of soils to be sampled in 2022. In this work, I present some of the results of this profile sampled in 2022. This is the eastern profile located at the base of the main pyramid of Templo Mayor. It corresponds to Operation 44, and in this place, the archaeologists, they identify three floors, three firms, and 17 fields. Besides, we have samples for the offering 182, where they found 8 children's skulls, and where they observed a different texture of the soil inside and around the skulls. Thanks to this information, we want to know what happened with the materials in all the profile and especially in the offering, and registered all the characteristics of the fields, floors, and firms. The methodology was followed was firstly the field work, where the profile was described to describe the characteristics of the different fields, floors, and firms. In addition, samples were collected for physical and chemical analysis, and also samples for the micromorphology analysis. In the second stage was laboratory, where we determine colorimetry, pH, and granulometry. Additionally, the unaltered blocks were prepared to make the thin sheets to the micromorphological study. So now we have the results only for 4 fields and 2 samples inside the skulls of the offering 182. I chose these fields and samples only for the short time that I have now, and because we have some important elements that in some cases don't appear in other fields or floors in all the profile. In the case of the granulometry, we can observe in the upper part textures with almost equal proportions of sand, silt, and clay. In the case of the field 14 is where we can see the difference, where the most abundant particle size is silt. The skull samples here, sample 18 and 137, the samples are in general very different. They are very sandy. We don't have silt. That is the reason for the texture change that the archaeologist mentioned before. For the pH, they are alkaline. We also see the difference with the skull samples that are more neutral than the other samples in all the profile. In the case of the micromorphology results, I present to you from the deepest field to the less deep. First, the field 14 has subangular structure, rock fragments, roots, and many fragments of charcoal, which can be seen in this photograph. Glacial characteristics of water saturation can be observed too. It is important to tell you that phreatic level of the subsoil in Mexico City is rise constantly and very quickly. These files, as well as the fields below it, present more natural characteristics, unlike the ones above which, as we will see more anthropogenic. The samples inside the skulls in the offering 182 show that there is not much structure in the aggregates, and it is more massive. There are fragments of carbonates and many remains of shells. There are volcanic glass, small rock fragments, especially basalt, and many charcoal fragments. In addition, the atoms were observed, which tell us that the material is also of lacustrine origin. Something important about these samples is that we can observe a reddish coloration, which we only observe in these samples and in the field 10, which is the one I show you below. This field 10 had something very particular. A massive material of the upper part of the brown color with rock fragments, quartz, roots, and shell fragments. In the central part, it had a strip of finer material that surely had a lacustrine origin because it had many complete and allinean olites. The material looks layered that we can see in this photograph in the right. Below that strip, the material is very compact, reddish in color, very thin material, and has some iron oxide. It seems probably to be born. In film 2, there are many shell fragments, carbonates, and some desiccation clots of the ground that are not aligned. Surely material brought from another place and arranged to be the preparation of floor 3. And finally, in the floor 3, where you can see lake materials such as olites and shell fragments, additionally volcanic material as rock fragments of basalt and tesontle, also fragments of stucco. In addition to the micromorphology, other analyses were carried out thanks to the presence of sub-elements like charcoal. So we decide to scan all the thin sheets, for example, in the sample 137 of the offering, as we observed in the slide, the abundance of charcoal was very peculiar. Some of them have an alignment as if they have prepared the space to put the skulls, the children's skulls. The fragments were of good size, so with the help of a good expert colleague, characteristic features of the charcoals could be identified under different phases, transverse and tangential. In this image, here, we see an example of the current circus at the bottom of, In this image, we can see an example of the current circus, and at the bottom, close-up in the petrographic microscope of the sample 137 that we have here, this one. And it was possible to identify that it was the same type of tree quercus. This allows us to recognize the Mexica's choice of materials for an offering, since these specimens were found in places further away from the banks of the lake. And that also, it implies a special job to take them to the ceremonial site. Another important element to know the origin of the material were the atoms, elements that were not found in the entire profile, but are less in abundance in fields 7, 10, and 14, and in the floor preparation surface. As we can see in the slide, I show you the 5 most abundant types of the atoms, like Denticula elegans, Coconace placentula, Flagellaria brevistriata, y Navicula reinardi. These 4 are from freshwater specimens, and one of them, this one, Flagellaria punta extriata, is from the transition from the freshwater to salt water, which was probably brought with the material from the east of the Texcoco Lake or the north of this lake of the Xaltocan and Zumpango lakes. But then, what is the reason for the use and choice of materials from the Mexicas? In this scheme, we can see how they use both materials. They had nearby and the material from the lake. That is why the presence of shell fragments, material from the banks of the lake, with the presence of oolites, and finally the volcanic materials from sites more distant like basalts and tezontle, and the wood used for offerings. The selection and placement of materials shows a construction technique known as the tlateles. This system was widely used in almost all the settlements in the Mexican basin, and it was a very efficient technology where the material was aided intentionally to create occupation surface, as can be seen in the and we can see this construction system in this slide when the person added material to create this occupation surface.
Yeah, it's important to
For finally considerations, we can see that the Mexicas use 2 types of materials, lacustrine material and volcanic materials. That they not choice only nearby materials, to choice materials from other parts like the wood of the atoms. We have elements of anthropogenic origin as the construction of tlateles to create occupation surface, but in the deepest part of the profile, lake characteristics, that tell us about a soil of natural origin. Finally, the study of the pedosedimentary records in Templo Mayor allowed to characterize the natural changes and the anthropogenic alterations that totally or partially modify the environment of ancient societies before, during, and after the affectation, as the selection and modification of materials used as construction materials. And that's all. Thank you for your attention.
Thank you for your presentation. Do we have questions? Maybe we have time for one question.
Yeah, we have time for question because Alena Sechkova cannot present. She has actually a 1 month child and
Case, but first the question.
she doesn't allow her to present now. Sorry, she's very, very sorry about it.
We all understand.
Yeah, me too.
But in this case, I can see that Daisy Valera is fast, so I would like to ask maybe next presenter just to keep the agenda more or less in time, yes?
And we have the.
But we have in time now.
Yeah.
Yeah, I mean, I also have questions.
A word on the very last slide, and she used it earlier in the presentation. What is that? How do you say it? And what is it?
Tania, do you want to explain what the tlatel is? The shell, the archaeologist.
Yes, of course. The tlateles was a system, a construction system that the name is, I'm sorry. The name is in Nahuatl, tlateli, that means in the mounds of air of islets or in the lake, no? That consists that the material was aggregate in some place and construct building platforms, sorry, to that it was used to building the temples of the pyramids of the yes, pyramids of buildings above this surface. Sorry.
Thank you.
So constructed mounds.
Yes.
Yeah, I have two short questions, actually. Probably I just didn't get how the charcoal or tissue of Quercus appeared inside the skull.
Some of the charcoals are inside the skulls, but the charcoals was like a bed to put the skull.
Oh, yeah.
To put the skull. It's a preparation to put the skulls, and probably after to put the skulls, burn this space like offering to the gods.
Yeah, thank you. And another short question. I'm pretty sure that you know why you measured the pH here, but please explain us how the data on pH was applied for this study.
I don't hear the last part.
Why?
Tania, ¿por qué medimos el pH? Si puedes explicar, por favor.
Please. Sorry. It's I don't remember the name of the machine that I use, but
no, it was not about the method, but about the reason. Why have you done it?
Is pH important for your conclusions, for your analysis?
How have you applied it?
I don't hear.
Okay.
Yes. Another question.
There is
Okay.
another question.
Okay,
No, there.
Yes, please ask your question.
Marty.
Hello.
Yes.
I can't hear. No.
Can you explain what types of mollusk shell you observed in the study area?
The mollusk. So the fragments of shells. Yes.
Yes.
Yes. Which species of mollusk shells do you have in your study area?
Okay. Well, I don't know exactly where is the specimens of this one. Maybe we can to study in the future, because only I observe the thin sheets and see these fragments. Only I can say that is from lacustrine origin, but I don't know exactly where is the specimen.
Thank you.
Thank you.
Maybe additional question? Maybe some additional remarks? No? So, thank you very much once again for the presentation. If one person is missing, one presentation missing, so probably we start.
We have the break.
Just start one time because
So thank you very much. We will start at 3 at our 3. Yes.
I'll start at 4 o'clock. Oh no, actually.
Hola, hi. It's really difficult to hear you guys. Okay, I'm going to share the screen.
Share your presentation. Yes.
Okay.
Okay. Yes. Change to slideshow. Yes.
It's okay now?
Yes, but could you change to slideshow?
If it's delayed.
At the bottom.
Yes.
Okay.
I already do it, but it's slow, I guess.
Yeah.
Okay, I'm going to start now. Yes.
15 minutes.
Yeah.
Okay. Hi, everyone. Thank you for having me. Okay, this presentation is related with the formation of pedogenic carbonates in the Teotihuacan Valley and their paleoenvironmental implications. I want to mention first that the pedogenic carbonates can be formed within soil profile developed of parent material like limestone, but also they can be formed in different parent materials with calcium carbonates under the right conditions, and the sources of calcium can be lithogenic for the parental material, or maybe they can be atmospherics related with this dust input. Related with this, the aims of these works in the Teotihuacan Valley was to identify the calcium sources for the formation of these pedogenic carbonates, to analyze the paleosoils properties in the Teotihuacan Valley, different profiles of paleosoils, and the relation of these paleosoils with the carbonates, and finally provide complementary information about paleoclimatic reconstruction in the region, because the Teotihuacan Valley is in central Mexico. We have a lot of another records like lake records, and within that combine these carbonates, pedogenic carbonates record with another record is important to have a better idea about the paleoclimatic conditions in the region. Okay, this I present here the Teotihuacan Valley in central Mexico, specifically in the Trans-Mexican volcanic belt,
and the different profile that we sample and we analyze in this study. This valley is constituted by the alluvial sediments and volcanic rocks with the andesitic basaltic composition. This valley have a semi-arid climate, and it's important to mention that in the high position of the landscape, in the high position of the landscape, we have a lower temperature and more amount of precipitations, and in the valley is less cold. And in this valley, we have soils like feocems, vertisols, cambisols, leptosols, and fluvisols. Specifically, we identify these layers of pedogenic carbonates in the luvisol and the vertisols paleosoil profiles. And here in this slide, I want to show the different the profiles in the Cerro Gordo volcano in the highest part of the landscape. And we have these different, it's a polygenetic soil. We have these two polygenetic soils with different horizon, and it's easy to identify these carbonates filling the cracks in this material on this horizon, that we named as tepetate. Is a cemented volcanic material. And yeah, in the Cerro Gordo profile, we also have these carbonates in the bottom horizons between the 2 CK and 3 CK horizon. We have this alluvial material also impregnated with pedogenic carbonates. The other profile that we sample, is a Maseca 1 profile, and it's a bigger one in the lower part of the valley, and yeah, also polygenetic. And it's interesting to see that we have different horizon here with clay alluviation and reductomorphic features like this 2 BTG and 3 BTG horizon. Oh, and even we have this 4 BTG horizon. And in the upper part of the profile, we have this BK horizon, and in the bottom, we have this CK horizon too. And I want to show now the different observations that we make in these thin sessions. First, in the Cerro Gordo profile 1, and in the horizon BC TK. And we identified this clay alluviation, but also the weathering of these minerals like pyroxene and plagioclasts. And also we identified these iron oxides. And we also make observations in these two specific nodules in the lower part of this Cerro Gordo 1 profile, and we can see this different layer of esperite and micrite in the nodule, but also this small inclusion of the soil materials and the carbonates also in some cracks of the plagioclase. And in the cave of the CG2 nodule, we find this micrite cement and this spiritic crystal cemented this clay in the profile. And moving to the observation of these pedogenic carbonates in and the difference in the Maseca profile, the different soils in horizon in the Maseca profile, we have this BK horizon, also with this weathered plagioclasts, and we have this carbonate that we identify like MS1, is a laminar cross, and we have these different layers of micrite, gray, brown, and white In some pores, we identify this spiritic crystal, and also in pore we have this needle fiber of calcite. And it's interesting to notice the difference with the horizons in the more lower positions, and we have this big change, and we can see this illuviation of clay in the pores, this iron and manganese oxide in the ground mass, and also this clay illuviation with the laminations, and also these weathered minerals. We see the same in this and the other horizons in the lower part of the Maseka profile, more clay illuviation, and it's important to see this cyclicity between the presence of the appearance of these pedogenic carbonates and the horizon with these really important clay illuviation features. And in the bottom of the profile, we have this specific type of well-developed pedogenic carbonate with these big crystals. And related with this observation in think session, we try to identify what happened with the plagioclases and what is the sources of this calcium for the pedogenic carbonate. And this method was really useful because we check in specifically these grains of plagioclase, and we identify these weathered features like twin planes and dissolution peaks. And this is important because we find this in the whole horizons of the three profile for this study. And we also made this observation of the content of calcite and low magnesium calcite in this pedogenic carbonate. And finally, we said that the mineralogy obtained for the seed concretion of the Cerro Gordo and Maseka profile were similar, with only a slightly difference between the proportion of pure calcite and low magnesium calcite. In the modern soil, we have pure calcite, and this concretion or nodules of with pure calcite, and the older ones have a small amount of low magnesium calcite. And also thinking about this aim to trying to identify the sources and try to somehow avoid the problem of this atmospheric input, this dust input in our pedogenic carbonates. We make this comparison between the strontium ratio, the isotopic ratio for our pedogenic carbonates and other samples like Arizona dust samples, New Mexico dust samples, and the value for the Trans-Mexican volcanic belt rocks. And finally, we identified that our samples are more related or have this similar signature that another soils in the Teotihuacan Valley, but it's not related with these values for the dust. But we think this contribution cannot be discarded, but it's not so evident in our case. And for the paleoclimatic reconstruction or paleoenvironmental information, we also made this chronology, and we correlate our profile CG1, CG2, and MIS1 with another studies in the area. And finally, we identified three different periods for the formation of this pedogenic carbonate. The first one for the marine isotopic stage 3, with age between 43,500 to 20,500. The second stage during the MIS2, with the age run is 27,000 to 20,500, and finally the last stage of formation of pedogenic carbonate from the middle to the late Holocene, with age from 5,000 to 2,500. And we also check these values of delta carbon 13, and we correlate and try to make a reconstruction of paleovegetation. And we see that we have this slight change. For the marine isotope stage 3, we have mixed vegetation, but this change for the marine isotope stage 1, and we have a more amount of C4 plants. And I want to make these final comments. The first one related with the sources of calcium for the pedogenic carbonate. Okay, the origin of the Teotihuacan Valley pedogenic carbonate could be attributed to the migration of water rich in calcium ions through the profile and the subsequent precipitation. And the source for these calcium ions was attributed to the weathering of these calcium-rich primary silicates like plagioclases. And this is also pointed for this observation of electronic microscopy. And related with the paleoclimatic condition, the radiocarbon age of this carbonate analyzed with a larger set of data for previous investigation in the area were used to establish a time frame corresponding to MIS3, early MIS2, and mid-late Holocene. And the micromorphological observation point to the cyclicity of this humid and arid climate period. If you remember the thin section slide, was really interesting. See these layers with a lot of clay elevation, and these layers of this horizon with the precipitation of pedogenic carbonates. And finally, the Pleistocene carbonates present a delta carbon 13 value, indicating these coexistences between C3 and C4 plants. But in the Holocene carbonates, we have this mixed vegetation, but with a higher proportion of C4 plants. That's it. Thank you for your attention. And if you want to check with more, if you have interest in this topic related with pedogenic carbonate, this is a publication related with this carbonates in the Teotihuacan Valley in Quaternary International. Thank you.
Thank you very much for your presentation. Also indication of the paper. We can extend our knowledge. We have time for questions, so please ask.
Daisy, I really like to talk, but can you tell us how much calcium carbonate there is in that profile?
Sorry, it's really difficult to hear you guys.
How much calcium?
Yeah.
Just wait. How much calcium carbonate do you have in those soils?
Well, it's not a lot. It's if you are focused only in this concretion or these nodules, we only have a BK horizon in the Maseca 1 profile, but we don't have a lot of carbonate, but because of that, we've tried to identify the sources. Exactly, because this point is not a limestone place with limestone, for example. And yeah, you can only identify these nodules or these, in some places, concretions.
Well, understanding the mass of calcium carbonate in the soil would give you some idea, and you've got the age of the soil, so you've got some idea about the calcium flux, and that might help give you an idea about the potential sources of that dust, or not dust, sorry, sources of carbonate.
Mm-hmm. Sorry, what's the question?
And so at the moment, the point is, if you knew how much calcium carbonate was in those soils, in relation to the mass of the soil itself, like 20% of it is carbonate or whatever it might be.
I don't make this exactly analysis, of course, but I can say that maybe 10% related with the whole profile. 10% of the accumulation of these calcium carbonates. They
make 10% in the ground mass, but the study was concentrated in the compressions, rise of compressions, nodules.
Sure, but the total mass of carbonate will give you some idea about what your potential sources could be. But how do you get that much calcium carbonate into the soil?
Yeah, the stoichiometric analysis was not done.
No.
I mean, it's very hard to make statements about the origin if you don't know how much, and so if there's a reasonable assumption or not, I think, anyway.
Well, in the field work, we identified these carbonates, and we know that they are carbonates, and we try to find the sources. And what sources we have in the Teotihuacan Valley, we try to make this analysis in strontium, because maybe the source is Aeolian, but we did not identify this relation. And yeah, the second dot was to try to find the minerals in the rock of the Teotihuacan Valley, and this andesitic basaltic rock. And we identified these weathering features in the plagioclasts, and we think that that is the source of the calcium for our pathogenic carbonates.
Okay, as I remember, you told about the various soils and they identified in this area, and you did not talk about any calcic horizons. So it is also indication that the total content is not very high.
Yeah.
Because calcic would influence the classification.
I mean, it can't disperse throughout the profiles and doesn't form a strong horizon. And that also would suggest that you don't have strong weathering going on if you're not getting clear horizonations.
Okay. Do we have another question? Yes, Maria?
Yeah, thank you, Dave, for your presentation. I have a short question. I've seen in your presentation horizons indexed as BTK. My question is, it means that there are pedogenic carbonates and arginals together, to my understanding. My question is, do you have any idea, was it formed simultaneously, or you can macrobiologically recognize phases of the accumulation of carbonates and arginals? Thank you.
Yeah, okay, Maria, if I understand right. Yeah, this is no simultaneous. Yes, we have these horizons with, in any case, we have this, well, in Cerro Gordo profile, we have this CTK, but we put K because we have this carbonate in this, I don't know how to say, this cracket in the tepetate. It's not in the ground mass of the soil, but we put this K denomination of for these carbonates in the cracket, not in the ground mass. And of course, we don't have the illuviation of clay at the pedogenic carbonate formation at the same stage, in the same moment. These two phenomena are contradictory somehow, don't happen at the same moment. Because we have water for one, for clay illuviation, and we have this evaporation process for the formation of pedogenic carbonates. But seeing these horizons in the field, we put this two T and K in the horizon because we find this in a specific, this I don't know, this these carbonates in the crackers of the tepetate. I don't know if I right.
Probably it means that first clay migration and after that carbonate accumulation.
Exactly.
If you have the carbonates in the cracks, yeah.
Exactly.
We'll stay with this.
Thank you very much once again.
And the next speaker is Maria Kotka. We have your presentation on our computer. Here. Yes, could we open it? It was open, as I remember. You stay here. You will be. Say. And we have microphones ready.
Which one is that?
It's okay. What's your name?
Name is here.
Maria Kotka.
Do you see it in the? Can you show me, please? This one? New Mexico.
New Mexico. Okay, so the floor is yours, 15 minutes. Yes?
I'll try.
It is. Okay.
The one and stage of paleogenesis. Our topic, stage of paleogenesis in the central part of East European plain within the top stage 2 and 3, archaeological site Epidova first, of Epidova 1. The last glaciation of Pleistocene has many names, Wisconsin, Valdai, Würm. Unfortunately, the problems are also many.
I'm sorry, just can I share this quickly to the Zoom people?
Okay. I'll try. Thank you. And I'm sorry, I will be reading because I'm so nervous and. Oh. Start? Again? Start. Okay. Stage of paleogenesis in the central part of the East European plain within isotope stage 2 and 3, at the lower 1 archaeological site. The last glaciation of the Pleistocene was many names: Wisconsin, Valdai, Würm. Actually, the problem are also many. Very especially many questions related to reconstruction of paleolandscape during the long and complex stage 3. Is it possible to answer? Is it possible to answer some of these questions with help of paleosoils?
Here.
What's my problem? No more.
No, it's not your problem, it's kind of my problem. They told me that, yeah, we use this window and then should be this window, screen 2. But I don't know screen 2.
Yeah, there you go.
Now share. Okay. Which one is this? Can you see your side?
The left side. Yes, this one. Not my last name. Just good. Name.
Thank you.
Now it is here.
It's earlier now?
Yeah.
Okay. Then you can
Start again or next?
Now you have it, Maria?
Yes. Yeah.
Yeah. Also changed?
Okay.
Okay.
For example, in Eastern Europe, stage 3 soils are represented mainly by on one soil level and often including modern soil. Meanwhile, in soil itself described by cryogenic wedges, and cryogenic wedges, and yes, this is a result of cryogenic occurring in LGM, but even so, these soils maintain an characteristic appearance to the wedge aggregation. In this, in Western Europe, European soil sedimentary sequence, several stage 3, are often seen, and these soil are not always disturbed by genesis.
Doesn't work? Sorry, not changing.
Not change. Yeah. Okay. Is a correlation possible between the soil?
Is it okay?
Not change. Oh,
yeah.
Okay. So the object of our study is Middle Paleolithic archaeological site Metrak M, located in central part of East European plain in the upper course of Desna River. Metrak is a multi-layered complex of Middle Paleolithic sites. They vary in extent of preservation of cultural horizon, located within 1 kilometer along the right bank of Desna River. Today we present just one, of course, with units section 3. The relief is composed of deep ravines intersecting a high river terrace. The geological composition is rock from late Cretaceous present by Cenomanian sand, interbedded with Tutorian marble, rocks with concretion of flint.
Very slow. Yeah.
Okay.
Oh.
This is a photo of full section. The thickness of the entry profile is 20 meters. This very soil sedimentary sequence of last glacial epoch, which are underlain by Cenomanian sands. As I said, the section is represented by a deposit of the last glaciation. In the bottom part of the section, early glacial and interstitial soils within them are described. The unit is overfolded by marble chunks. The age of deposits between 77 and 85,000 years, and here's 2 paleosols described here also. It is in this part of section and in the same deposit in other Metrak M section, but Middle Paleolithic layer are located. In recognition of our archaeologists, here's few slides with the finds. Stone Bifas were found in 2023, and another unique find in 2023 was fragment of Bifas in a large herbivore mammoth engraved in form of zigzags and individual curved lines. This is a very rare evidence of the symbolic behavior of Neanderthals. Okay, let's go back to our drawing. In the upper part, in the upper part, the section is as a soil sedimentary sequence of middle glaciation, and loess-like loams of the late Goryachkin and modern alluvial soil formed them. In this work, focus on soil sedimentary sequence of stage 2 and 3. The thickness of this unit about 4 meters. It is composed of 4 independent soil levels. The very bottom soil of the series, soil 4, is a very well preserved unregulated soil, over 1.5 meter thick, with 5 genetic horizon. The age of this soil, 34,000 calibrated years. As the soil underbedded this is sediment, which was a deposit from higher level. This soil, the bottom horizon BCK is a layered, very sandy, and Catalinas from BK are seen in upper part. And horizon BK is most features here is Catalinas. On micro level here, there is iron manganese nodules with dendritic morphology. There is many primary carbonates and micro nodules. Horizon BW, brown and alloys. The clay coating and iron nodules inside are seen. Horizon AO and E present as fin, deposit 20-30 centimeters thick lenses, and horizon is partly charred. Microphology, indistically humus aggregation of forest organo-mineral horizon and charcoal fragments. Upper, we have 3 layer soils. Soil 3, and the soil is brown and humidified with a sedimentary soil about 0.5 meter thick. The aim is that 27,000 calibrated years. It is disturbed in small wedge in upper part, and in the lower part the length of underlying sand. On micro level, there are sand grain clusters and genetic microstructure, large loads, and capping in center. Soil 2. Soil, another poorly developed glaze soil consisting of 2 pedogenic layers separated by loess-like loams. Soil level similar and color and density inhibiting homogeneous terrain. This section do not have alloys. There is no structure. The mass is compact. There is a sign of glaciation due to water saturation above permafrost in iron manganese paper coating and many spheres. And last one, soil 1, weakly developed and thin but visible on all section wall. The soil inherits feature from the underlying loess-like loams. This paleosoil strongly clade, cryogenic deformation are absent on the macro level, but we see a lenticular structure due to ice lancing upon macromorphology description and the coarse material with sign of cryogenics in present. Next, we will show you some data from physicochemical results. This is a graph of granulometric composition of soil sedimentary sequence, where an expected high content of coarse silt in the first two thin soil formate in loess-like loams. Curiously, in soil 3 and 4 is a high content, especially in Cambric horizon soil 4. It should be noted that in central part of the sediment, the silt fraction correspond to horizon AO, and in sample collected above and below there is high sand content, which is a result of inverse soil. Next, we have a magnetic cortex, the peak for magnetic susceptibility in a horizon of soil 4. And iron ditonite, the peak fall on horizon AO and BW on as well on the pediment of horizon AO. The relationship of ditonite to the total iron maximal in sand horizon and horizon BW. And last graph of carbon content. Where expect peak in the carbonate horizon of soil 4. So the section we presented today in the central part of East European plain. The soil sedimentary sequence in our section does not have notable geogenic changes. This may be to high thickness, over 5 meters, embedded loess-like loams, which preserve all paleosols. We can correlate with soils. Cambric soils in Khatelova resemble MIS3. Cambric soils, gray soil areas correlate with European tundra clay of MIS3 and MIS2 transition. Thank you.
Thank you very much. We can start because we are connection.
Yeah.
There is no message.
Nobody listen.
Last time I checked.
Okay, so thank you for the questions. Yes.
Thank you, Maria. Very nice presentation. I would love to know if
macromorphology, but maybe much new thing. But a little bit, but nothing. When we used acid, nothing. I'm sorry for.
This is not a scientific question, but the power, did you do all this on PowerPoint? You know, the way you converted the profile picture and an image, and was all that done on PowerPoint, or how did you do the artistic?
But his doesn't work. I'm sorry. I never do like this. Because it doesn't work.
Нет. Слушайте, в чем, как ты делала вот эти вот то, что отрисовки?
I can show you. I can show.
Okay.
PowerPoint, in PowerPoint.
Is it PowerPoint?
In PowerPoint, in PowerPoint. That was nice.
And this area is divided into 3 zones: the lowlands from the north, the lowlands from the south, and the highlands. All this space was occupied by the Mayas. And here you can see where Palenque is situated. Palenque is a Maya city founded around 150 AD, according to the archaeological studies. This city expanded during a time period of nearly 500 years. And to construct the city, it was the necessity to alter the landscape, to modify this landscape, and also to bring a lot of different kind of materials. You can see the area, and all the buildings are made of stones. So this is one of the
Your screen is low.
Okay, meanwhile, this problem is solving. I can say that in this area, we are in the boundary of two physiographic regions. One is the Sierra Madre de Chiapas, that is mainly constituted by folded limestones and sandstone. And here we have the Usumacinta region. This is one of the main rivers in Mexico. So this is a very big basin going through Gulf of Mexico. So when we started this work, we have the idea that we will find rendzines or terra rosa soils, because in our previous soil survey, we were working in another archaeological site. The name of this site is Chiniquija. And in this site, we have seen many rendzinas and terra rosas. But here, we started our survey because one of the main questions we had was, what's the soil cover available for the Mayas to construct the site? Finally, so now very quickly, you can see here is the Usumacinta Basin, and this is Sierra de Chiapas, and the nowadays conditions in the area are very humid climate with 3,000 millimeters of precipitation and very hot, very high temperature around 30 degrees. So this is these are the questions of our research. How was the soil cover previous to the occupation? What kind of materials the Mayas used for the construction of the site? As Tania has already explained during her presentation, in the Mesoamerica region, the construction of the sites was in different stages. So first, building was built, and then it was covered and leveled, and then another building was constructed. Lose connection?
Because of.
Yeah.
Okay.
Okay.
Okay, Elizabeth, can you keep talking and we'll.
Yeah, okay. So one of the main things that we did was geomorphological analysis using LiDAR and visualization techniques, but I have to be very honest, I haven't done this work, so this is from my student. And if you want to know more precisely the method, I can't explain. So in identification of the construction materials in one specific building of one group of buildings in the area, and the soil profiles analysis around this. Of course, we did micromorphology and micromorphometry. So the first result I have is the geomorphological map made by my student.
Yeah, I would go ahead and show her presentation.
It's important to show the map.
Yeah. I should share it by Zoom. That's fine.
Yeah, I know, but for right now, let Elizabeth. Yeah. That's okay. Just go ahead and let her get the presentation. Yeah.
Oh, okay.
Okay.
Yeah.
So this is the geomorphological map, and Paleolake is located in this rectangle, and this is the Usumacinta Basin, and these are the main features of the Sierra de Chiapas. And what you can see here is a modification of the relief to construct the city. The Mayas leveled the relief to put the constructions. They deviate some of the main rivers in order to have canals for water supply, not only for agriculture, but for drinking water. And also they extracted a lot of materials for the construction of the buildings. And what I said is that we started with the idea to find terra rosas and renzinas, but actually there were no terra rosas. Instead of them, we have found these sandy soils, silty soils, excuse me, derived from these siltstones. And we have found this soil not only in the natural profiles, but you will see that it is under the constructions. And only one side we have seen a rensic type soil, but you will see the properties of this soil that are not suitable for a renzine. And these are the thin sections. You can see this is from the natural soils, a dominance of sand and silt material made of quartz and plagioclases and micas, but there is accumulation of clay elevation, and then we see that these soils are not rensic type. They are not terra rosas, but they have clay cutans. It is important to say that even in the rensic type soil, we observed silty particles from these sands, from these limestones, from these siltstones and sandstones. And this is the building that we have studied. And in there, the building, we have analyzed 4 profiles that, according to the archaeologists, represent the different stages of construction of the site. And what is important to mention is that this building was dedicated to funerary activities, because many burials of people were found here. So this is one of the fields. You can see this is the yellowish soil with this silty material that we have observed in the natural soils, with clay orientation, but in the upper part of the field, we have this sand accumulation and siltstone fragments. We also have shells and accumulation of carbonates. In other of the fields, we have seen stucco materials. We have also, this is another kind of carbonate that is travertine. The source of this travertine is very close because we have the rivers going down to the main Usumacinta basin, but also these clay cutans that are mixed with the main soils and other kind of carbonates. This is another field. You can see here the wall made of stone. And here we have also the stucco material, another stucco, carbonates of different origin, charcoal particles. And we date materials found here, and it is 200 to 350 AD. So it represents a medium stage in the middle period of the construction of the site. As we haven't noticed many differences between the different materials that we analyzed according to the periods, what we tried to do was a morphometric analysis. So these are the thin sections, scanned and analyzed. And what you can see here is, for instance, the soil-related features are marked in yellowish and these reddish colors. And then we have here limestones, travertine, stucco, charcoal, the ceramic, and bones. With this analysis, we could see that there were differences among the different infills we analyzed. And then in the bottom natural soil under the construction, there is only one piece of travertine, some bones, and some soil-related features. In the first and second field from the side, we observe that we have more travertine, more charcoal in this layer, but in the third layer, we don't have travertines. So this means probably that the Mayas used different kind of materials according to what they have available. And what's interesting is that we have here bones in the natural soil, but this is because from this material, burial was recovered by Luis Núñez in the moment that we were sampling the site. So the grain size distribution also shows something, because we have here in the natural profiles a dominance of silty materials. But you can see here that even in the forensic soil, we don't have a lot of clay. It is the domain of silty materials. So actually, there are no forensic soils in the area, but nowadays, you can see the forensic soils on the top of the constructions that are abandoned. That means that the limestone of the constructions are contributing to the formation of these kind of soils. And these are the granulometry of the construction fields. They are very similar to the natural profiles. That means that they took the materials from the surrounding soils and they mixed with other specific anthropogenic materials from natural and not natural origin. So in summary, Palenque was built basically on these silty soils, which were used for the construction of the site. And now the renzinas are more related to the buildings. For the construction, it was necessary to make changes in the landscape, as I have already shown. There are similarities among the materials, but the morphometric analysis helped us to differentiate the stages of the construction. And then what we have seen is that travertine was used as material construction. We don't know why. If we think like archaeologists, we can put some philosophical considerations, because talking to archaeologists, they said, oh, they wanted to represent water, fire, and heaven. And then they used this kind of materials for this representation. Maybe yes, maybe not. And then what is real is that the deviation of the rivers caused also a deviation of the travertine findings, because now you have the river crossing the Palenque area, and you can see the travertines in the area. But if you move from another side, you can see also the travertines from the past. So these are the preliminary study that we have, and thank you for your attention.
Thank you very much for this interesting presentation. Question? Yes, please.
Joe,
Joe.
can you explain a little more the formation of the Renzinas next to are they adjacent to the buildings? Are they next to the?
All the buildings, because yes, all the buildings, yes, yes. This is the parent material, limestone, the parent material of the Renzinas, that is quite known. Maybe in the future we will have terra rosa.
So I like this statement that you call this formation soils, regions, because there is a large discussion are such formations soils or not. Yes, and there are diffisols sometimes called on the buildings. Yes.
Yeah, maybe we can put the name of archisols in the new classification.
It is the starting point for a long discussion.
Yes, yes.
We call them natural ranginas, but still edifisols, soils and buildings.
Yeah,
But you were
very general question. Did they burn lime in order to make mortar?
Yes.
To make the stucco, and did they use mortar in the buildings?
Yes.
Okay.
Yes. Yes.
So you said they're using travel construction? Where were they getting the travel? What's coming from?
Oh, in the river. It is just around.
Picture.
Yes, here.
Oh, so these are spraying from the out of the river?
This is the river. This is not exactly from Palenque because I didn't have a photo from the side, but thank you. This is very close from very close to Palenque, but yeah, well, here in this river, which we collected this soil here in the river bank, but inside the river we could see different kind of materials travertinized, even cans, spoons that are abandoned in the river and they are completely calcified. So the process is going on.
But do you believe the formation of travertine is possible in such a large water flow?
It is. I have seen. I have seen it.
Okay. When the streams get on the air, they get gas.
Yes, they get
Spectacular examples in Western.
You should try to reconnect.
Huge travel Paris with a lot of rivers.
So.
Farming questions.
Cover living education. Travis is the one.
10 minutes.
I've never seen a travel before.
Yeah.
It's forming along a river where there's lots of springs.
Right.
Is it traveling to need the biomass? Films
and this small cascade, all the formation is travertine. Yeah, travertine.
So finally, which soils dominate the
Here, around Palenque are these silty soils. I didn't want to enter in the classification only because I am there.
Because for me, what is interesting that if we try to classify soils, so we have to check also if they look naturally or maybe they are deformed by like I don't know, excavation, transportation or something. And for me it was also interesting. Are the soils more or less natural, state preserved still, or they just developed recently after the abandonment?
No, I think that they are natural preserved soils and they have illuviation. So because of the illuviation, can we name them as illuviation?
Because you told it was very maybe not large, but active towns, so we may expect large activity of people, not only on in buildings, but also in surrounding areas. So they also influence the
Yes.
soils.
Yes, but the same soil we have found under the constructions. Identical soil. So this is why we are sure that this is the natural soil previous to the construction of Palenque, and the rest of the natural soils are in the surrounding.
Because as you know, it is another story, but we finished already this session, but there is a new discussion how long time we need to recover naturality of, for example, ecosystems of forests. Yes, this discussion was in Amazon, yes, probably also in Central America, but we also have this discussion in Poland, and some people say 800 years under temperate climate, 500 years, but recently we found new data that maybe even 200-300 years is enough to allow large variability, differentiation of soils and ecosystems, and the recovering of naturality of soils. Ecosystems. So it is interesting, how to say, discussion. What about soils surrounding the abandoned places, abandoned some centuries ago?
Yes, and what is interesting is that in this folded range, Sierra de Chiapas, you have mainly limestones, but in the side, there is sandstone and siltstone that is in the center of anticline, but now they are on the surface. Because of the...
I was just gonna say, I think it's hard to find.
It's okay now. Can I share? Try to share? Can you bring your call? Okay.
There you go. Once again, thank you very much. And it was last presentation in this session. Yes, Maria, you are controlling our agenda. So now the break for coffee. So we start the next session at according to agenda. We have to simplify 10 minutes or 4:30.
40, okay.
15 minutes, yes? Okay, so 4:30 we start the next session.
You already
switched for break.
We have an internet.
Now I'm gonna just ask them if they are seeing the. You are still
Because next are my colleagues.
Let's talk to her or ask your question.
Yes, I ask Linda.
Yeah, but I mean,
And then we share her slide.
Yes, she was going to. The microphone is on. Pamela, ¿nos escuchas? Está bien, solo estamos probando. Entonces, en 10 minutitos vamos a comenzar. Espero que haya suficiente internet como para que no se bloquee nada.
Ok.
Perfecto. Los 10 minutos.
I try, yes, I'm Jolly Kumari and I should see, so I stop sharing the slide now. I just remove her slide, stop sharing. Yeah.
Kumari and yes.
No, he will not.
Tajikistan, Botswana,
Please, okay, now I asked. I will check. Yeah, my student. She said it's okay now.
Okay.
This kind of stuff is.
Yeah.
Always problem. No.
They are.
I'm sorry. Somewhere I've done the changes, but I don't know. Yeah, I don't remember where. In this option, the version.
Maybe it's the clay.
And then simulation process.
I mean, I think that when I think of this, that's what so whatever it is.
Yes, protocol. Yeah, I think it should.
Paleofeatures.
Yeah, should be.
Yes.
Let me double check it.
Yes, I can see. Sol Moreno Rosso is also connected with us. So I will have.
I have a question.
Oh, yeah. Yeah.
About your talk yesterday.
We answer it a little bit later. I'm trying to figure out how the program, just, yeah.
Yeah, no problem at all.
Like, yeah,
we've got
we'll be
dates.
together,
We've
yes,
got
yes,
dates.
yeah. I'm so sorry.
No,
Trying
it's no
to
problem.
figure out what the program. Подожди, мне нужно понять, подальше доход, мне подожди, я не про то. Я про то. Сейчас, хорошо, если у кого-то, сейчас, ладно, это так, спрошу Никиту, в конце концов, правда, они отвечают.
Somehow I can't follow this direction.
Oh, yes.
Yes. So she after I think. And Sol will be tomorrow after the round table.
Okay. So.
That'd be a all right, great.
So, shall we start?
Yeah.
Yeah, okay. Please, I hope this time we will not have troubles with the connection.
Yeah. Can you see my video? I mean, can you see me on the screen?
Yes, perfectly well.
Actually, I can see myself on the screen, so I just asked this.
You see the slides?
Yeah, I can see the slide, but I can't see myself. Should I stop the video or it is okay with this?
It's okay.
Okay, don't worry.
Okay. Now I'll start. Okay. Now, can I start?
Yes, please.
Please.
Okay. Hello, everyone. I'm really sorry for the interruption again and again, but now I'll start my presentation. And the topic of my presentation is Paleosol narratives, reading diagenetic and pedogenetic imprints in Lametta Formation, Central India. Next, please. Can you hear me? Okay. As we all know that the Paleosol is one of the best proxy to reconstruct paleo environment. But one of the persistent challenges in studying Paleosol is the diagenesis. In the buried Paleosol, as the Paleosol got buried, its pedogenic characteristics got diagenetically modified. And it is very important to distinguish between the pedogenetic and diagenetic characteristics of the Paleosol to reconstruct the paleo environment. So basically, I have used this can you please change the slide? Yeah. So basically, I have used this proxy Paleosol, and I have studied keenly its digenetic and pedogenetic characteristics based upon morphology and micromorphology. I have studied these paleosols present in late Cretaceous sediments of central India, which is presently as the Lamata Formation. Lamata Formation is very famous for its dinosaur fossil fauna of India and its close affinity with the Deccan Traps. Deccan Trap is continental flood basalt of KT boundary. Can you next please? Stratigraphically, as I have told you earlier, that Lamata Formation is overlain by Deccan flows. It is infratrapian with context to the Deccan Traps, and it is divisible into 4 litho units. I have studied the paleosol in lower limestone and mortar nodular bed unit of Lamata Formation. Next, please. This is the geological map of the study area. Star locations are the 4 locations which I have studied for paleosols, and I have studied paleosol and its micromorphology, morphology, and I have studied basically 9 paleosol profiles in these 4 localities, and divided that these paleosols into 5 pedotypes based upon the maturity of the pedogenic characteristics of these paleosols. Next, please. As I have told you earlier about approach of my study, that the basic approach is the dividation of these paleosol into a pedotype based upon their maturity. And just as that, the pedotype 1 is the least mature paleosol, and pedotype 5 is the highly mature paleosol. And based upon these paleosol, I have tried to reconstruct the paleo landscape of the Lamata Formation. Next, please. Now I will come to the pedotypes that I have divided, in which I have divided the studied paleosols. Pedotype 1, as I have told you earlier, is the weakly developed paleosols. The basic character of these paleosols, the basic character of these paleosols is the presence of soil structures. As in the soil lithologue, we can see the lowermost horizon is VWS horizon, which represents the presence of soil structures. But there is not a prominent presence of alluvial features which can represent mature paleosols. So these paleosols are weakly developed, and I have classified them, these paleosols, as proto-soils based upon the McAltol 1993 classification, which is particular to the paleosols. Next, please. These are some representative field and microscopic photographs of the pedotype 1. In figure A, we can see that we can clearly see the presence of subangular blocky ped structures in these paleosols. And the presence of carbonate nodules is also visible in the figure A, which is represented with the red ellipse. And in figure B, we can see the subangular blocky microstructures, which represents the VW horizon. And figure D, we can see the presence of a micritic nodule, which is represented with the N. Figure C and E are the XPL of above figures. Next, please. This table summarizes the micromorphological and morphological features of the pedotype 1. And based upon these features, we have concluded that these paleosols are weakly developed, deposited in poorly drained environment. Next, please. Now coming to the pedotype 2, which is better developed as compared to the pedotype 1. A is the field photograph of the paleosol, and B is the soil profile of this. The basic character of pedotype 2 is the presence of carbonate, is the accumulation of carbonate in the form of concretes and nodules. As we can see this in the lower panel of the photographs, figure A, B, and C. The carbonate nodules and concretions are shown with the pink ellipse. Next, please. Yeah. These are some micromorphological photographs of the pedotype 2. As I have told earlier, that the presence of carbonate nodules in the form of micritic nodules or concretions is the basic character of this pedotype. We can see the carbonate nodule in figure A, figure C, F and I. And figure D represents the presence of subangular blocky pets, and figure G represents the presence of partially decomposed organic matter. In figure H, we can see the ferruginous hypocoating around the quartz grains. Next, please. In this table, we have summarized the morphological and micromorphological features of the pedotype 2. As told earlier that the presence of carbonate is a basic character, so the presence of decay horizon is also obvious that in these paleosols. And based upon these morphological and micromorphological features, we have divided these paleosol into moderately developed hydromorphic calcisols. Next, please. Now coming to the pedotype 3, which is better developed as compared to the pedotype 2. And figure A is the field photograph of paleosol pedotype 3. And in these pedotype, the basic character is the presence of a glade horizon at the lower part of the profile, followed by BSD horizon at the upper part. Next, please. These are some micromorphological photographs in which we can see the presence of we can see the presence of carbonate nodule in figure A, D, E, and G. The presence of ferruginous infilling within the planar voids can be seen in figure B. Figure C is the axial of figure B. The presence of highly separated subangular blocky pits can be seen in figure F. There is also one of the basic character of these pedotypes is that the presence of rhizolith, large rhizolith that can be seen in figure H and I. The presence of rhizolith is also one of the prominent character of pedotype 3. Next, please. Yeah. This is again the summarization of morphological and micromorphological features. And based upon these features, we have classified these paleosol as moderately developed, moderately drained paleosol. Moderately drained paleosol because we can see that the paleosol, the above horizon of the paleosol is BST, which indicate the leaching, and the lowermost horizon is BCD, which indicates that this horizon is under the water saturated at least for some time. Next, please. Now coming to the pedotype 4. I forgot to tell you in the earlier slide that we have find pedogenic characteristic, prominent pedogenetic characteristic in the previous pedotypes, but there was not any prominent digenetic character in that pedotype. But in pedotype 4, we can see a prominent digenetic character in these paleosols. This is the field photograph of the paleosol, and field photograph of the paleosol, and this paleosol is better developed as compared to the previous one. We can see this by the well-developed horizonation in these paleosols. Next, please. The micromorphological feature of these paleosol is indicated in this photograph. A represents the presence of ferruginous nodule. B and C represents the ferruginous hypocoating around the quartz grains. And whereas you can see in figure G, we can see the presence of chalcedony, which represents the diagenesis, which represents the diagenetic character. The diagenetic character can also seen in figure H and I. The subangular quartz, which is surrounded by spiritic calcite. Presence of spiritic calcite is represent diagenetic modification. Next, please. Next, in this figure A and B represent ferruginous nodule. Figure C represents the presence of biogenic excrement. D is the axial of the C. Next, please. Yeah. As I told you earlier that only these pedotype 4 represent prominent digenetic features. That and in these photographs we can clearly see the diagenetic feature. In figure A we can see the presence of chalcedony, that is microcrystalline quartz, and the figure B is the PPL of A, and in figure C we can see that paleolithic calcitic cementation, which is diagenetic feature, and D is the PPL of the C. Next please. In this table, we have summarized the micromorphological and morphological features of these pedotypes, and based upon these pedotypes, we have classified them as moderately well-developed paleosol with significant diagenesis. Next, please. Now coming to the pedotype 4, which is a highly mature pedotype as compared to the previous one. This is well-developed pedotype. And we can see this in the well-developed horizonation and presence of DST horizon. This is the field photograph of the pedotype 5. Next, please. Next, the presence of rhizolis as mottled structures surrounded by the reddish brown rim is one of the basic character of these paleosols. As we can see these structures in figure A and figure B. Figure C represents the sub-angular to sub-rounded blocky pet structure. One of the most prominent character of these pedotype is the presence of alluvial clay. We can see this in the figure D. The presence of alluvial clay pedofeature. And in this figure D, the red ellipse represents the ferruginous hypocoating around quartz grain. In figure D, we can see the calcitic hypocoating around the quartz grain. F represents the subangular to sub-rounded blocky microstructures, and D represents the aggregate ferruginous nodule. Next, please. Yeah. This A figure represents the cyst oxide segregation, and figure B represents the presence of plant material, partially decomposed plant material, which is represented with the yellow arrows. Figure C represents the clay alluvial features present as the infilling within the planar void, and figure D is the XPL of A. Next, please. So this is the summarized table of the figure pedotype 5. In this, similar to the previous pedotype, in this pedotype we did not find any prominent diagenetic feature in these pedotypes, and based upon the morphological and micromorphological feature present in these pedotypes, these are classified as well-developed pedotype forms on moderately well-drained environment. Next, please. Paleoenvironmental implication. Based upon these studied pedotype, we have firstly, as I have told you earlier, the interpretation of these pedotype. These pedotype are based upon the pedofeature that we have identified in these pedotype. These represent the compound and composite paleosol profile, and that are composed of weakly developed proto-soils, that is pedotype 1, moderately developed hydromorphic calcisol, that is pedotype 2, glade argilly soil, pedotype 3, and the well-developed argilly soils, that is pedotype 5. Based upon these pedotypes, we have tried to reconstruct the paleo landscape of the study area, in which the better drained paleosol form the high grounds and the poorly drained paleosol form the lowland. And based upon these studies, we have reconstructed, we have tried to reconstruct the paleo landscape as agglomeration of seasonal wetland and dryland. Okay, thank you so much. I'm done. Yeah. Any question?
Who is the convener?
I'm so, is there any questions?
Yeah.
Is there any questions to Anjali? Yes.
Actually, I can't see anybody on the
Yes,
screen,
correct.
but
It's
I can.
yeah, Sputnik. It's Sputnik. Turn on the camera. PS prize.
I thought it was.
What is PS prize, Anjali?
Accumulation of iron oxide. That's what I'm. Yeah.
Iron, yes.
It wasn't
I can't
really-
hear you clearly.
Maybe somebody can ask.
Она просто повторит еще раз, Маша. Yeah, what is BS horizon, Anjali?
Sorry.
BS
I can't hear you. Can
Do you hear?
BST horizon.
Yes. Yes.
BST horizon, there is an accumulation of cyst oxide and alluvial
Yeah.
clay. BST horizon.
Yeah, okay. Do you have any questions? Yes, please.
Maybe you said it, but the Lamita sediments, I'm not sure I'm pronouncing it right, but when were they deposited?
They are late Cretaceous sediment, mass recent in age.
Late Cretaceous.
Late Cretaceous, yeah.
Yeah. Yeah.
More questions? I have a short question for you. You shown us the not crystals, but accumulations of opal. Is it diagenic accumulations or pedogenic? Or if pedogenic, what was the process which formed it?
Can you please repeat the question?
Opal deposits. In pores, you shown us opal.
Opal. Okay. Microcrystalline silica.
Microcrystalline silica.
Yes, it's silica. I mean,
Yeah. Okay.
Yes, yeah, it was about the process.
Actually, this formation is just below the Deccan Traps. So the studies, the previous studies have concluded that this silica may be due to the presence of Deccan Traps. This may be leached from the Deccan Traps to this formation.
Diagenic. Yeah, it means. Yes. Thank you so much.
Yes.
Thank you.
Thank you. Thank you so much. Thank you so much.
So the next presenter is Garcia Pamela, please. Can you hear us, Garcia?
Yes.
Pamela. Yes, oh, excuse me. Pamela, yeah. Could you?
Yes.
Could you share your screen?
I'm doing it.
Yeah, thank you.
Share.
Yes. You can see. Thank you.
Okay. Should I start?
Yes.
Okay. Thank you for allowing me to be here. My name is Pamela, and I'm a PhD student. And I'm going to present you some of preliminary results of a ongoing investigation between the paleosoils group in the UNAM and the archaeological project of Chocohabutuha. This work is focused on the biodiversity of Maya agrosystems, and it's just what we did in this past summer. So we don't have a lot of results, but we have some interesting findings that we want to share. So our study area is here in Mexico, and we are in the state of Chiapas, close to where the Dr. Elizabeth presented. She's in this area of Palenque, and we are here in the frontier with Guatemala. We are in a landscape that is folded limestones that are producing this mountainous karstic landscape. And we are in a tropical area, and we also are inside of what is the most active zone of the Mayas in the classic period, right? We don't have big, well, we have like 2 or 3 big sites, but we're not gonna talk about these important sites of this dynastic politics, but we are gonna focus on the main
The archaeological group has done like around 10 years of research in the area, and they have found through survey, walking survey, and also through LIDAR, the settlement pattern of the area. And what we can see in this settlement pattern is that most of the activities, most of the structures, architectonical structures of stone are found in the upper parts of the terrain, of the mountains, of the sierras, but also on the hills in smaller elevations. In the lower parts, in the valleys, we don't have this evidence of big constructions. And so we assume that most of the activities are taking place in the upper parts of the terrain. And then we need to think about, well, where are they getting this food, right? Where is the agriculture? If all the society activities or day-to-day activities are taking place in the upper parts of the terrain, well, probably the agriculture is taking place in the lower parts of the terrain, right, in the valley. We have found some evidence of different types of plants consumed by these people, these habitants, but this evidence in the phytoliths, macrorest, and starch are mostly found in secondary deposits. So constructional fields or like trash cans, well, where you put all the trash, and not on the soils, right? So, like I said, where is the agriculture taking place? Well, there are two possible places. One is the channelized fields in the lower parts of the terrain, but also in the slopes of these mountains, we have terraces. The thing with terraces is that they seem to be more like habitational than to produce surplus of food. Maybe they are growing some stuff there, but it's more like a home garden, like you produce some of your food and you consume it locally to your family. So we thought that mostly they must have been doing the majority of the agriculture in these lower parts, in the channelized fields. Now, as part of this questioning of the agriculture, we have they have done suitability models in which they have, I think, are like 18 kind of plants. They are grouped based on growth preferences, and they have done a model with this based on the slope, on the percentage clay, and the water available capacity, the available water capacity in the soil. The problem, or one of the important things to note about this model, is that if we have some characteristics of the soil, like the clay and the water capacity, but we don't have a lot of the soil, right? So we want to feed more information to this model to make it more precise. And also this model has not been checked ground, it's just been proposed. I think it was a result from past year or something like that. So there hasn't been much work around this. So, like I said, I'm going to present you what we did during this field season, this past June. And we did some research on the lower areas in the channels. In the area of Nuevo Canán, here are the channels, and the area of Busilhacho, Costa Rica. These two areas are areas that are flooded for most part of the year, but this time they were not flooded, so we focus our work in these areas. And we're going to focus a little bit more in the Nuevo Canán area, because Busilhacho, Costa Rica has already been studied a little bit more, and probably some of you have seen some of these results in other congresses. So just very quickly, the Butsilhal, Costa Rica area, what we have is glacial type of soils that has the characteristics of having these gypsum accumulations in the lower parts. There are not like we cannot explain easily that they are growing or they are forming here in this tropical environment, right? And another thing to have in consideration of this area is it's very close to an archaeological site. We even have a stone alignment, like a pathway, that permits the communication between the archaeological site and the agricultural areas, right? Whether in Nuevo Canaan, we don't have any of this. We don't have an archaeological site close, and we don't have a stone structure around. And we don't have these deep soils that we show in here, right? Instead, we have these very shallow soils, like 30 centimeters around. And we have the presence of this carbonated layer, like stopping the formation of the soils that we thought was like the Saskap, the limestone with some decomposition, with some degradation. And we thought, well, the topography of this Saskap, of this limestone layer, is these little holes, in the topography, right? But we also found these bigger and more shaped, orientated excavations that we assume are anthropic, right? And they are being excavated to create these channelized fields. So what we can see in this profile is we have big accumulation of clay in the soil in the upper horizons, these papules, but also in the matrix we have this clay, and we also have these charcoal fragments. They are more of a woody type material that is not, we don't think is growing here on top of this soil, right? We also have the presence of iron nodules, and in the lower parts, in contact with this carbonated layer, we have the presence of the carbonated matrix with clay papules and some other fragments of soils, more darker, more humic, probably. So this is the soil that we found in this area. Another excavation have shown the same soil, and then we did another, and we found the same, right? The layer, the carbonated layer, and the shallow soil of 30 centimeters with the excavation of these channels. Now, we thought this was the limestone, but one of our collaborators took a walk around the place and found this, maybe it's not very clear, but it's an alga, right? An algae. And what under this is on top of the grass, and just below the grass in soil, we can see this precipitation of carbonate material, right? So now we don't think this is natural. This is not part of the bioform or the layers of the natural layers. Well, it is, but it is not. And it is more like a secondary deposit of carbonates, right? For this algae periphyton. And so we did another, we didn't want to destroy the channel, so we did another profile here to see what is happening. And here is what we have. In the channel, we have the formation of two layers of organic matter. This is the grass on top, then a horizon, then another grass formation, and then another hay horizon, and then we have a a layer of borne material, and then we have an AB horizon, right? Now, the borne material that we have is more, the charcoal that we find here is more, is not woody, it's more like what they will have burned on top and then stay there, right? Like one of the practices of the agriculture of Mesoamerica is like burning and leaving the stuff in there. Then in the lower part, we have similar to what we have in the other profile, carbonated matrix with clay and other fragments of soil. If we follow to the other profile, what we have is the presence of these two big accumulation of carbonated material, and under this precipitation, we have the formation or some major accumulation of organic matter. Now here we have this organic matter, layers of organic matter, and then we have these shells and goes like layering, right? But also in other places, we found this carbonated matrix with some material that is a little bit more with petogenesis, and that presents some of these colorations of a horizon. So the soil here is not completely forming an A horizon, but is in the process of making. And how do we explain the formation of this type of profiles of this type of soils? Is that probably we have this area that is usually flooded with the presence of the periphyton algae. There is making the allowing the precipitation of the carbonates, and it's at some point we don't have that much water, we don't have so much production of this carbonated precipitation, and then we have another moment that has more precipitation, less accumulation of organic matter, but we still have some layerings here of organic matter, and then we have another moment where we have more presence of water, more precipitation of carbonated material. And then we have the Maya occupation on top of this, right? Creating these channels and these burning layers on top of in the area of the channels. Now, something interesting to explain, or something that is maybe important, is how these soils have this much clay, right? So what we are proposing is that material, this is the area of Canaan, and it's just right beside this mountainous, this sierra. And so we are thinking that the material on top of this, where probably we have some settlements of the Mayas, we haven't found, I think the archaeological team doesn't have much information about the occupation of this area, but following the settlement that we saw early, we will have the activity here, then we will have some erosion from the soil on top of this, and goes and deposits in the lower parts, giving these characteristics of charcoal. There is charcoal, there is woody, and also from this big accumulation of clay material, right? So we have done some other studies to complete to understand these agriculture properties of this possibility of areas of our agriculture. We have done some studies about the capacity of the soil, and we are trying to compare the soils. These are soils profiles on top of the terrain in the terraces around here, and soils in the lower parts of the terrain. And we are doing this analysis in the upper parts of the the soil, like the surface, but also in the parts where we thought that maybe the Mayas were more active, right? Or have more yes, these soils are more perturbed or like more modern, to say some way, and these are the ones that we think the Mayas would be at there. And so what we want to do with this is like make these soil maps where we have different type of soils with this type of information, not only the type of soil, but some of the characteristics of these soils regarding agricultural and plant necessities and stuff, and do these new suitability models. And that's all. Thank you.
Thank you so much. Any questions? Yes, please, Peter.
Are the terraces human constructed or are they natural terraces?
No, human constructed.
Okay. And then my second question, and maybe I'm just confused, but you're showing that light gray layer in the subsoil and it's calcareous, and you're talking about precipitation. Is that the secondary? Yeah, I like that profile, the CK. So that is mostly limey material, or is it mud that's impregnated with lime?
No, this is just calcium carbonate, secondary calcium carbonate precipitated by hydromorphic processes of these algae.
More questions?
Is that indurated or is it easy? Is it soft?
Sorry, could you repeat?
Soft.
Is it soft or hard?
It's horizon.
Horizon.
Soft.
Yes.
It's soft. It's like lime. No, sand. Wait. Silt. It's a silt material. Silty material. It's easy to carve for the blocks.
Is there any questions?
Primary or secondary sediment?
She said that it's secondary. Accumulated from the
waters. It is in fact kind of the jelly.
not in water. Was it accumulated in water or from groundwater? The calcium carbonate in this fraction. I mean,
sorry, I don't think I.
Lithotrenic or accumulated from groundwater.
I think it's a combination of groundwater and the water that comes from this place and just stocks like here for a period of time.
From lateral, probably.
I'm not saying, I'm saying there couldn't make a distinction between paleogenic and groundwater. It can be paleogenic.
Because I think that a lot of questions arises because you index this horizon as CK. That means that C is the parent material and K like pedogenic feature.
Yeah.
So that's why we are asking what is the. So is it pedogenic or formed in the at sedimentation stage?
Yes, this maybe was my mistake. Sorry. We said that this was a CK when we thought this was just the soil that we found. So we said that this soil, the parent material is this, and this is the limestone that is there. But now we think this is just a sea horizon because it's the parent material of this soil, but also there has the accumulation of carbonate calcium from hydromorphic processes. So I'm not sure what would be the sub-index of this if it's not.
Okay.
But is it 100% calcium carbonate?
Yes, here's the thin section that is not very thin, but we have just micro well, calcium carbonate very small, and just some traces of organic matter that you could see like around here, but it's not.
Okay. And it should be, it shouldn't be purely pedogenic, it should be probably both pedogenic and lithogenic. Okay, thank you. It's so interesting.